As we begin this CISSP training, one of the first things we have to realize from a practical standpoint and from an exam standpoint is that ISC² will expect us to know and adhere to a code of professional ethics. As we can see here, all information security professionals who are certified by ISC² recognize that such certification is a privilege that must be both earned and maintained. In support of this principle, all ISC² members are required to commit to fully support the Code of Ethics, otherwise known as the Code. ISC² members who intentionally or knowingly violate any provision of the Code will be subject to action by a peer review panel, which may result in the revocation of certification. ISC² members are obligated to follow the ethics complaint procedure upon observing any action by an ISC² member that breaches the code. Failure to do so may be considered a breach of the code pursuant to Canon 4. It would be helpful on the exam to memorize the Code of Ethics preamble. The safety and welfare of society and the common good, duty to our principles and to each other, requires that we adhere and be seen to adhere to the highest ethical standards of behavior. Therefore, strict adherence to this code is a condition of certification. Also on the exam, be able to answer questions that regard the Code of Ethics canons. There are 4 of them. Canon 1, protect society, the common good, necessary public trust and confidence, and the infrastructure. Canon 2, act honorably, honestly, justly, responsibly, and legally. Canon 3, provide diligent and competent service to principals. 4, advance and protect the profession. In this lesson, we'll explore the distinctives of the 2 different CISSP exams. First, we have the CAT exam. CAT is computerized adaptive testing, and CISSP uses CAT for all English exams. The length of the English exam, or the CAT, is 3 hours. The computerized adaptive testing exam is made up of multiple choice and advanced innovative item question types, for example, drag and drop. The passing grade is 700 out of 1,000 points. The exam language availability for the CAT is English, and you can take the exam at authorized PPC, Pearson Professional Center, and PVTC, Pearson VUE Authorized Test Centers, and select Pearson VUE Testing Centers. The CISSP linear exam is administered as a linear fixed form exam. The exam language availability for the linear is French, German, Brazilian Portuguese, Spanish Modern, Japanese, Simplified Chinese, and Korean. It's made up of multiple choice and advanced innovative item type questions, such as drag and drop. The length of the linear exam is 6 hours, as opposed to 3 hours for the computerized exam. The passing grade is the same, 700 out of 1,000 points. And you can take the CISSP linear exam at authorized PPC and PVTC select Pearson VUE testing centers. Let's look at the domains and the examination weightings of the CISSP 2021 exam. They're actually very similar to the CISSP 2018 exam. The domains are the same, and the weightings have only been slightly changed. Domain 1 is Security and Risk Management, making up the largest amount of the exam, 15%. Domain 2 is Asset Security, making up 10% of the exam. Domain 2 and Domain 8, Software Development Security, are the 2 smallest domains of the exam. Domain 3 is Security Architecture and Network Security, 13%. Domain 4 is Communication and Network Security, 14%. Identity and Access Management, IAM, 13%. The Security Assessment and Testing domain is 12%. And Domain 7, Security Operations, is 13%. On CISSP 2018, Software Development Security was 9%. In the new version, 2021, it's been raised to 10%. In Course 1, ISC Squared in the CISSP exam, you learned about the ISC Squared Code of Professional Ethics, the 4 Code of Ethics canons, the computerized and linear exam information, and the CISSP examination weightings of the CISSP Common Body of Knowledge, 8 domains. In the next course, you'll look at key core security goals and principles, the OSI reference model, and the TCP/IP reference model. We have a number of goals in security, and to meet those goals, we're going to introduce controls to raise the level of difficulty or create resistance for threat actors and threat agents. One of the primary goals is confidentiality. Confidentiality measures the attacker's ability to get unauthorized data or access to information from an application or a system. And realize here we're mentioning unauthorized data or access. Somebody could still be authentic and be authorized, but not be able to actually see the data or use the application or system because of confidentiality mechanisms. In other words, they don't possess the right credentials or key. Confidentiality involves using techniques, most often cryptographic mechanisms, to allow only approved users the ability to view sensitive information. And of course, it goes beyond just viewing the information. It could be writing the data or using the application or the system. And notice that we often use cryptography, but not always. We can use tools like compartmentalization, encapsulation, and other methods to provide confidentiality. The confidential information could include the passwords themselves, or passphrases, cryptographic keys like session keys. For instance, we might use an asymmetric key crypto system to protect symmetric session keys. PII, personally identifiable information, such as a national ID number, social security number, passport information, and other background information, personal health information, data that should remain private for compliance to regulations and governance, intellectual property of a company or an organization, such as formulas, marketing campaigns, corporate secrets, and other information. And if it's a certain type of information that has classification and sensitivity levels, it could be secret or top secret information as well. As a candidate for CISSP, we need to go beyond just basic confidentiality mechanisms and consider some of the high-level confidentiality controls. For example, using hybrid encryption, involving combinations of symmetric and asymmetric crypto systems. For example, in SMIME, where we use algorithms for confidentiality and digital signatures for origin authentication and non-repudiation. We can employ advanced post-quantum encryption as an ongoing countermeasure against quantum cryptography, and homomorphic crypto systems to protect data in use. For example, information in a Redis in-memory storage cluster. And high-level confidentiality can combine secure compartmentalization with the most recent modes of encryption available, for example, on your upgraded iPhone or mobile device. Confidentiality represents the C of the CIA triad. Coming up next, we'll look at the I in the CIA triad, and that's integrity. Integrity represents the I of the CIA triad. At this point in our security careers, we've moved well beyond just the basic checksum as an integrity mechanism. For example, the frame check sequence in the trailer of an Ethernet frame, or the checksum that's performed when you move or copy a file from one volume to another. Integrity security measures an attacker's ability to manipulate, modify, change, or remove specifically data at rest and/or data in transit. Realizing that the data at rest could be configuration of applications or systems. Integrity involves implementing the controls that make certain only authorized subjects can change sensitive information. Realize that integrity might also include affirming the identity of a communication peer, in other words, origin authentication. In fact, the A of the CIA triad doesn't stand for authenticity or authentication. Therefore, the origin authentication is often combined with the integrity mechanism in the form of a hashed message authentication code, for example, SHA-1 or SHA-2 HMACs. Other examples of a breach of integrity would be injection or hijacking attacks on data in transit, modifying files, changing access control lists, corrupting route tables on routers, and DNS or ARP cache poisoning. Let's talk about high-level integrity. In other words, going beyond just protection from unauthorized modification or changes. Later on in this training, we'll talk about mandatory access control. And in that MAC architecture, there's a Clark-Wilson model. Clark-Wilson has advanced goals for integrity. Obviously, we want to prevent unauthorized users from making modifications. However, Clark-Wilson goes further to ensure separation of duties, preventing even an authorized user from making improper modifications. Clark-Wilson ensures well-formed transactions and maintains internal and external consistency. As an experienced security practitioner, it's important to understand mechanisms and techniques for delivering high levels of integrity at the enterprise level, not just for the small to medium-sized business, but for large enterprises as well, both on premises and in the cloud. Availability is the A of the CIA triad, and it measures an attacker's ability to disrupt or prevent access to services or data. Availability controls will protect systems and services from spoofing attacks, floods, denial of service or distributed denial of service, poisoning, and other attacks that negatively affect the ability to deliver data, content, or services. Vulnerabilities that impact availability can affect hardware, software, firmware, and network resources. Examples would be flooding network bandwidth, consuming large amounts of memory on a server, for example, a front-end web server, or a relational database management system, stealing CPU cycles, or unnecessary power consumption, to name a few. As a CISSP candidate, we want to think about high-level availability. For example, understanding how availability zones work at cloud service providers, such as Amazon Web Services, Google Cloud Platform, or Microsoft Azure. The big three, according to Gartner. Each availability zone will have at least one data center. The availability zones are tens of miles apart. Lessons we've learned from the past are to make sure that our high availability or our disaster recovery solution involves sites that are not across the street from each other, but rather many miles apart, often on a fiber network. For example, in the Amazon Web Services Northern Virginia region, there are 6 availability zones, all of them tens of miles apart. They're connected with high-speed fiber, in other words, metropolitan area networks. And cloud service providers provide high availability and durability by placing data centers in regions all over the world. And an organization can replicate their data or their services in a multi-regional model. This is also done to distribute through content delivery or content distribution networking services into metropolitan areas all over the world. You can also describe the goals of the CIA security triad by looking at the opposite, DAD. D, disclosure, is the unauthorized revealing of data and information, the opposite of confidentiality. A is the alteration, or unauthorized change or modification of data or systems, the opposite of integrity. And destruction involves rendering an entity inaccessible. It can also add the element of lack of durability in some scenarios. Destruction, or disposition, is the opposite of availability. In this lesson, I want to expand on the traditional CIA triad and take a look at Dr. Don Parker's Parkarian hexad. Parker expanded on the CIA by adding 3 additional elements. Let's take a look at those. First, Parker added authenticity. It's not uncommon for security practitioners to assume the A of CIA is for authenticity. However, A is for availability, as we learned earlier in this course. Parker added authenticity and made it part of his hexad. Authenticity refers to the accuracy and identity of the origin of the entity or the information or data. Authenticity is often tied to identity. And in modern information systems, we typically have more than one factor of authenticity. In other words, dual or multi-factor authentication. The next addition was utility, or usefulness. While an asset, such as data, would be confidential, controlled, integral, authentic, and available, it is not always useful or valuable in its form. So, for example, assets can lose value over time. As their value or utility diminishes, the need to introduce controls for confidentiality, authenticity, and availability become less valid. The third addition was possession. Possession is also referred to as control. An attacker takes possession or control of a physical or logical asset. That's true. They may do that, but it may not be a breach of confidentiality. For example, if an attacker steals a drive, but the data on the drive has been encrypted, the attacker may have possession, but they haven't breached confidentiality. If an attacker steals a standalone safe, they may have the safe, but they may not have possession of the contents of the safe if they're unable to crack that safe. We often deliver authenticity with technical controls, utility with administrative controls, and possession with physical controls. Let's take authenticity, an aspect of the Parkarian hexad, to another level. Remember, origin authentication is a basic form of authentication. It only provides a degree of confidence that the correct password, passphrase, or private or secret key was used. Additional levels of authentication rely on trusted third parties and certificates, digital signatures, and multiple factors like biometrics. A new trend in high-level authenticity is KBA, knowledge-based authentication. This is often accomplished by asking an entity a series of questions, often multiple-choice questions with 5 possibilities. This information basically comes from the taxpayer's personal history or financial history. For example, what color is your 2020 Honda Accord? What county or province is a particular address in? Has the party ever been associated with a particular business or a particular individual? If the subject or the entity answers the knowledge-based questions correctly, they're authenticated and further identified. It's important on the CISSP exam to be aware of the next waves of high-level authenticity and identification. In this brief lesson, we're going to look at the concept of non-repudiation. There's actually 5 pillars of information assurance. We've already talked about the other 4: availability, integrity, confidentiality, and authentication. Non-repudiation is the fifth, and it's defined as the inability to refuse participation in a digital transaction, contract, or communication. For example, email when SMIME is being used. Now here, refuse participation means to deny participation. So, we want to guarantee that a message transmission or a transaction or a contract between parties on the internet is guaranteed. We often accomplish this with crypto systems where a public and private key pair is used. In other words, non-repudiation is a level of assurance that the owner of a signature key pair that was actually used to generate an existing signature that corresponds to some type of data cannot convincingly deny that the data was signed. Therefore, it's the responsibility of the owner or creator of the private key to protect that key. You may attempt to repudiate or reject or deny that some transaction was valid or true. However, if your private key was used, you are responsible. Therefore, the owner or creator of a private key must notify the trusted third party or certificate authority when the key is lost, stolen, or compromised. The key could be on a smart card, it could be on a laptop, a personal device, a USB key or fob, or some other appliance. For the sake of the exam, remember that non-repudiation, in the context of information assurance, or IA, is typically accomplished with digitally signed certificates. If you look at the CISSP common body of knowledge and the different objectives, you'll notice that they want you to know about the ISO OSI reference model and the TCP/IP model. In this lesson, we're going to look at the 7-layer OSI model, something you're probably already familiar with. Now, obviously, memorizing these layers from the physical layer 1 up to layer 7 would be valuable, perhaps using a mnemonic. But from an exam standpoint, the important thing to remember is how security relates to these different layers. Now, if we go back in time to 1974, to the original protocol, all we had was the transmission control program. There were no layers, just one layer. And thanks to John Postel, we soon divided the TCP into TCP/IP. And of course, we have TCP and UDP at the transport layer 4, and we have IP at network layer 3. Now, the big takeaway here is that if we look at these different layers, and we look at the descriptions of these layers, one thing we realize is that natively, security is not built in, especially to functionality at layer 1 through 4. We have to use additional protocols or other extensible mechanisms to provide security, specifically at layers 2 through 4. As time passed, developers and programmers did give us security protocols and mechanisms. So a quick review: layer 1 is the physical layer that specifies our connectors, our data rates, the way that we encode bits, how to represent zeros and ones, our physical media, Ethernet, wireless, fiber. Layer 2 is the link layer, the communication across a single link, including media access control. The link layer has 2 sublayers. The top layer interfaces with the network layer 3, and the bottom layer interfaces with the physical layer 1. Layer 3 is the network or inter-network layer, facilitating multi-hop communications across potentially different link networks. In other words, forwarding IP packets, IP version 4 and or IP version 6. Layer 4 is the transport layer, connecting multiple programs on the same system, of course, using port numbers. Layer 5 was the session layer, and this is where developers began to introduce security protocols. For example, protocols that could be used with application layer protocols like HTTP. The session layer accommodates multiple session connections. Layer 6, the presentation layer, is there to help us express and translate data formats. We can also see some encryption at the presentation layer as well. And layer 7 is the application layer, to accomplish a networked user task. Remember, this is not all applications, but only applications and services that use the TCP/IP stack. In this table, we can find out more information about the protocols and services used at different layers. At layer 2, the link layer, we have protocols like PPP and its predecessor, SLIP. Like the link layer, PPP also has two sub-protocols, a protocol to interface with layer 3 and a protocol to interface with layer 1. We also have Ethernet, frame relay, and ATM at the link layer, as well as various device drivers. At layer 3, at the network layer, we have protocols like IP version 4 and version 6, Novell's IPX. We also have other protocols that assist IP, like ICMP, with its event and informational messages, and Address Resolution Protocol ARP, to resolve logical IP addresses to the MAC address of the link layer. We also have routing protocols at layer 3, like RIP version 2, OSPF, EIGRP, and BGP, Border Gateway Protocol. The transport layer has protocols like TCP and UDP, with its over 65,000 port numbers, Novell's SPX, and Apple's AppleTalk. At the session layer, we see SSL TLS. Today, we really use TLS almost always. We have SQL with its structured query language, RPC, and NFS. At the presentation layer, you may have encryption, but for the most part, it's there for translation, and other representations using mechanisms like ASCII, PNG for graphics, MPEG and AVI for movies, and MIDI, commonly used in music and film. And at the application layer, we have HTTP, FTP, SMTP, DNS, and Telnet. Notice none of those protocols has any native security. So typically we combine Secure Shell or SSL TLS with those protocols. So for example, if the protocol is SFTP, that's going to be Secure Shell 1 or 2 with FTP. If it's FTPS, it'll be FTP over SSL, or today, FTP with transport layer security. And of course, HTTPS is HTTP over SSL TLS. Later on in this training, when we talk about network security, we'll revisit these protocols and services. In the next lesson, we'll look at the 4-layer TCP/IP model, which is actually the model that we use most often today. If we think about reference models, it's actually quite rare to use the ISO OSI model today, even though we still use the terminology of like layer 2 for layer 2 devices or access switches, a layer 3 process, terms like that. Thanks to Microsoft, however, we now use a TCP/IP reference model that has 4 layers. So today, we combine the session, presentation, and application layers of OSI, layers 5, 6, and 7, into one application layer. In other words, most of the activities that happen in modern applications today that would be traditionally layer 5, 6, and 7 are combined and performed by the application, whether traditional programming or microservices or container. In the TCP/IP model from Microsoft, the physical layer 1 and the link layer were combined into a single network access layer. That's the physical medium, the network interface cards, and the device drivers. Layer 3 is the internet or internetwork layer. That still involves routed protocols like IP and AppleTalk, as well as routed protocols like OSPF and BGP. In IP version 4, we still use ARP, but we don't use ARP in IP version 6. As a matter of fact, IP version 6 relies heavily on ICMP version 6 and its additional messages to perform the activities that version 4 ARP performed. The transport layer is pretty much the same. However, you see it referred to as the host-to-host layer because one host using port numbers connects logically to another host using port numbers, specifically TCP and UDP. And of course, in the 4-layer model, We have layers 5, 6, and 7 of the OSI model combined into the top application layer. Although this is the model most commonly used today, on the exam, be aware of both the 4-layer TCP/IP model and the 7-layer ISO OSI model. Now, before we leave this discussion of reference models, the ISO OSI and the Microsoft TCP/IP model, you may have noticed the absence of a very important extensible protocol, one that operates at layer 3 of the OSI model and the internet or internetwork layer of the TCP/IP model, and that's IP security, IPsec. It goes without saying that's one of the most important protocols that we use in networking today, perhaps SSL/TLS being a close second, or in some cases, equally important. We'll have dedicated discussions of IPsec for IP version 4 and IP version 6 coming up in later courses. In this course, Fundamental Concepts and Principles, you learned about the CIA triad and other fundamental concepts like the Parkarian hexad and non-repudiation. You explored the OSI reference model and how it relates to security, and the TCP/IP reference model. In the next course, you'll explore secure design principles. The first concept we're going to review in this course is that of least privilege, probably one of the most important concepts to implement as a control in your environment, especially to countermeasure privileged insiders doing unauthorized actions. It's an aspect of authentication, authorization, and accounting, AAA, and identity and access management, IAM, where the subject has just the proper level or amount of permissions and rights to perform the job, role, or responsibility, and nothing more. These permissions can be granted directly to the subject or as part of membership in a group or a container. Least privilege should be built into all access control architectures. As a matter of fact, some architectures, like mandatory access control, take the concept of least privilege quite seriously, whereas in a discretionary access control environment or role-based, the implementation may be a little bit looser, with more responsibility given to the creator or owner of the object. Regardless, the principle should be at play at all times. Any deviation, escalation, or elevation from least privilege, if allowed, should go through an established change control IT service, or possibly a service desk implementation, and a change control model for standard, normal, and emergency changes. Least privilege is also referred to as need to know, staying within one's pay grade or classification level, especially involving architectures that have sensitivity levels, lattices, and different classifications like top secret and confidential. One of the documents you'll want to add to your knowledge base for the CISSP exam is the NIST Special Publication 800-53. NIST gives some examples of implementing least privilege in this document. They encourage us to authorize access to all security functions, in other words, auditing the auditors in many regards, or getting visibility into administrative security actions as a top priority. Use non-privileged accounts or roles when accessing non-security or low-level functions. In an Active Directory environment, many administrators have normal user accounts which they'll use on a regular basis, but then, when necessary, they will run as administrator. Or in a Linux environment, using sudo to change the context to a higher privilege level or a root user. We also want to prevent non-privileged users from executing any privileged functions. That should be built into the architecture. It also should be audited on a regular basis. For example, there are tools at Amazon Web Services that can do machine learning analysis of the ways in which identity and access management are deployed using JSON documents. And visibility is key. Audit the execution of any secure functions. There's also ISO IEC 27001, They have some examples of least privilege implementation. 27001 encourages us to get visibility into access to all networks and network services. This can involve a combination of firewall services, intrusion detection and intrusion prevention services, as well as endpoint protection and other logging and monitoring tools. They emphasize the management of privileged access rights. Using enterprise solutions like Cisco Identity Services Engine can help in this regard. Monitor and control the use of privileged utility programs. Only select users in your organization, high-level users, should be using vulnerability assessment tools, vulnerability scanners, and other penetration testing techniques. You want to control the installation of Type 2 hypervisors, where unauthorized programs and kits can be run. You also want to audit the usage of elevated or escalated privileges, like local administrator or root level privileges. It's vital that you manage access control to any and all program source code, whether it be traditional applications or containerized or microservices. Securing sites like GitHub and other code repositories is tantamount. In this lesson, we're going to look at the very important concept of defense in depth, or DID. Defense in depth is also referred to as layered defense. In the upcoming course, we'll talk about due diligence and due care. But at this point, realize that using the least privilege principle and defense in depth is a function of due care and ongoing continual improvement. DID should be systematically planned and designed with an outward-in approach or an inward-out approach. Defense in depth can be applied physically, for example, starting at the enterprise facility property line or the entryway to your building. It could be your floor in a high-rise building. But starting at the edge and working your way back to the keep, where the most valuable resources are, perhaps the data center, or a safe, or a locked closet in the CEO's office. This can also be done logically. Defense in depth with secure routers, firewalls, intrusion prevention system sensors, and layer 2 and multi-layer switch security. You can also take an inward-out approach as well. The most important thing is to be systematic about it. Defense in depth is also a common element of supply chain risk management, SCRM. Layered security is accomplished by end-to-end security using several components, both physical and logical. It could be a single appliance with multiple integrated engines operating on packets in an order of processing. They can be physical, they can be cloud-based, or virtual or logical. Layered security applies to networks, applications, and the physical facility as well. The trend of deperimeterization has increased the need for organizations protecting data and systems with defense in depth by implementing a combination of cryptographic schemes, using more secure protocols, using hardened systems, and next-generation access control and endpoint protection services. Defense in depth no longer totally depends on its DMZ, or public access zone network boundary to the Internet, and the various ISPs and ITSPs, basically removing the perimeter or outer security boundary. We also see defense in depth being accomplished using managed security service providers like Fortinet and FortiGate, or Palo Alto Networks or Cisco, as well as cloud access security brokers with software as a service providers. Let's get a visualization of defense in depth. In this example, we're going to start at the edge with perimeter security. Then we look at network security, endpoint security, application security, and data security. At the center are our mission-critical assets. We also want to have monitoring and response operations and prevention using policy management. Here we see defense in depth at the perimeter, using perimeter firewalls, intrusion detection and intrusion prevention systems, secure DMZs and public access zones, secure messaging, for example using email security appliances, or cloud-based email security for our message transfer agents. We'll deploy honeypots and honeynets. We'll also implement data loss prevention engines, such as the RSA DLP, and machine learning with DHS Einstein. Network security can be done with network admission control, NAC, inline patching, IDS and IPS for the enterprise, protection of voice over IP packets, also firewalls at the enclave and data center, web proxy content filtering, and web application firewalls, enterprise message security, for example, Cisco's ESA, enterprise wireless security, enterprise remote access, and again, data loss prevention or prevention of data leakage. Endpoint security goes beyond just host-based IDS and IPS. We have desktop firewalls and security suites. Endpoint security enforcement, for example, Palo Alto Networks Traps, or Cisco Advanced Malware Protection for endpoints. There's also content security, with security suites from vendors like Malwarebytes and Sophos, with antivirus and anti-malware solutions. We also have compliance on endpoints, for example, FDCC or HIPAA compliance. Several IT services come into play with endpoint security, for example, patch management, and of course, data loss prevention. Application security. Defense in depth also applies to application security, with static app testing, code review, database and secure gateways, database monitoring and scanning, database activity monitoring, DAM, dynamic app testing, and fuzz testing, and web application firewall to countermeasure cross-site scripting, SQL injection, cross-site request forgery, and other malware attacks. There are many solutions for data security. Of course, we have data loss prevention and data classification, but we can also introduce identity and access management, the next generation of AAA services. There's enterprise rights management, for example, through Cisco Identity Services Engine, data integrity monitoring, encryption, public key infrastructure, and data cleansing. Our next aspect of defense in depth is prevention through policy management, continuous improvement, risk management, vulnerability assessment and pen testing, threat modeling, cyber threat intelligence through the cloud, security awareness training, and secure architecture and design, and our subset of governance, IT security governance. In continual operations, we'll perform monitoring and response, monitoring our SOC, our Security Operations Center, and NOC, Network Operations Center, using SIEM systems, security information and security event management, incident reporting, detection and response, through the Cyber Incident Response Team, digital forensics, escalation management, security service level agreements, SLA and SLO reporting, using security dashboards for visibility, and continuous monitoring and assessment and situational awareness for mission-critical assets. That, in a nutshell, is defense in depth. Our next key security principle is separation of duties, SOD, also referred to as segregation of duties. Now, this is an important principle because it's often tied directly to compliance and regulations. So SOD violations could be a serious problem for your organization if you're in a violation of industry regulations, if you have government contracts, other types of entities. This is a principle where more than one entity is necessary or required to complete a particular task, such as a separate backup operators group and a data restoration group. You also see separation of duties in Agile and Spiral and CI/CD development, where you're dealing with containers, and microservices, where certain individuals will work on certain components or certain modules. It may be separating into developers, and then testers, and then the production team. It can be applied a lot of different ways. For the CISSP exam, however, it's more than just understanding how to define separation of duties. It's having kind of a management approach. All these principles demand that you have kind of an IT management approach and understanding and application. So we'll talk later in upcoming courses about the controls that we'll use to implement least privilege, for example, and defense in depth. But here, we want to think about SOD and that it may involve other principles like dual operator principles, where you have two or more subjects needed to modify or make a change or to provide approval. So, for example, two signatures or two different cryptographic keys are necessary, or tokens, for certain activities, certain actions. Rotation of duties is also a related principle to separation of duties, where you have different individuals rotating into a job role or responsibility after a certain period of time. Sometimes it'll be a random amount of time. The goal here is to reduce any type of single point of failure, any illegal activities, data theft, exfiltration, misuse of systems or applications, and it can involve, for example, mandatory time off or forced vacations of employees or certain employees. So the goal is to reduce, if not eliminate, your SOD violations. So from a management standpoint, we're going to have some automated tools. We want to have management of SOD, or segregation or separation of duties. In this particular example of automating this process, this is going to involve our IS security team, or Information Systems Security group, working in the Security Operations Center. I want to break this diagram up into three parts as we talk about it. But notice in the first part, where we're doing our application development and our application security model, that the output of that is going to go to the IS security team and the application or app control owners. And then the outputs of that particular team and the corrective actions they take will lead to making the correction. Okay, application administration, correcting user access, correcting role access, and so on. And then, of course, output to a dashboard where we'll do after actions reporting and lessons learned and improve the process. So regardless of the model that you're using for application development, whether it be Spiral or Agile or CI/CD, you're going to build security into that model. So it's DevSecOps. So on the IS security team, the auditors, the compliance managers, you'll have application access rules, part of your IAM. The rules manager may manage the application test environment. There, we'll use tools for extract, transform, and load, ETL, basically a data integration process that combines data from different sources, in this case, application developers working on containers or microservices, into a single consistent data store. And we'll take an application security snapshot of that. Now, from the application test environment, this is where our team is going to enforce separations of duty and do it in an automated way. So we have access analysis where we detect policy violations and SOD violations. We have a violations manager who will analyze those violations, often doing a gap analysis against regulations or compliance. So we've got our IS security team, but we also may have what we call app control owners involved in this process. Yes, there's going to be exceptions. Any exceptions to this will go through a change control process, maybe through a change control board, because there may be situations where you want to violate the SOD policy. It's not going to cause a compliance or regulations issue. It actually is going to improve the process. And of course, we're going to take corrective actions, and those corrective actions will be part of a workflow with approval, with iterative processes, and the output of the corrective actions is going to go to the application administrator, where you're going to correct the user access, you're going to correct the role access. So the roles can be part of your role-based access control methodology. It may be like a role or permissions assignment at a cloud provider, for example, where you are assigning permissions to different entities. The application administrator will then output this correction to a dashboard where that individual or other individuals as part of the IS security team will get visualization, will get ongoing monitoring and improvement, The dashboard should give reports that can be presented to other team members, escalated to C-suite or C-team. And again, the goal is continual improvement and a more mature security posture for your organization. So again, as we go through these different principles, remember for the CISSP exam, it's not simply just defining the principle or understanding the principle, it's understanding how we manage the implementation and deployment, integration, and improvement of these security principles. In this very short video, we're going to cover a concept that really needs to permeate all of the other concepts and technologies that we're talking about in this course. As a security practitioner, we must always find the delicate balance between security and protecting data, applications, and systems while still maintaining user productivity. The synergy between the security compliance and our organization's value proposition and our organizational charter or mission. Overcomplexity can often lead to configuration errors, and configuration errors are one of the most common vulnerabilities in systems and applications and in code development. Keeping it simple can also mean using automated tools and orchestration techniques, both on-prem and in the cloud. It can involve infrastructure as code, or using templates or predefined sources of truth in JSON and YAML documents. Keeping it simple often means using the obvious administrative, technical, and physical control within your budget. Here's an example of keeping it simple. If you have too complex of a password policy, that in itself can create vulnerability. You may think you're creating a more secure environment, and you're actually delivering the opposite. So for example, here's a password or a passphrase. I've got 3 7-letter words, bizarre, spandex, and dolphin, capitalizing the first letter and separated by a dot or a dash. This would take a computer about 700 sextillion years to brute force crack. However, organizations often force complex password policies on their employees. In this example, 13 characters, including uppercase, lowercase, numbers, and symbols. This looks complex, but actually, this would only take about 2 million years to crack. In other words, this is a much less secure password than 3 7-letter words that can be remembered. An end user will quite likely document the $G8 password on a sticky note or a text document, which in itself creates a vulnerability, whereas they could easily memorize 3 7-letter words separated by a dot or a dash. So as we apply the principles we've talked about so far, like least privilege and defense in depth, as well as other principles we'll look at the rest of this course, it's always important to remember at the heart to keep it simple, and don't forget about the basics. In this lesson, we're going to explore the zero trust principle, and again on the CISSP exam, we want to go beyond just definition and understanding, but also look at it from a management standpoint, a security management, information security administration standpoint. But to define it, zero trust is an evolving paradigm, moving focus to individual users, individual assets and resources. In other words, moving security down the OSI model close to the endpoint and layer 2. It uses zero trust principles, which means trust no one, trust nothing, to design industrial and enterprise infrastructure and technological and communication workflows. It assumes that no implicit trust is given to subjects based merely on their physical or their network location. In other words, just because they're located in the R&D department as opposed to the call center doesn't mean that we're going to implicitly trust them, nor do we implicitly trust the endpoint devices used by the C-suite or the C-team. Typically, we use zero trust network access solutions, for example, Cisco's Identity Services Engine, Microsoft's Zero Trust, and others, to perform authentication and authorization as a distinct task before the actual session is established. This can also be done through technologies like IEEE 802.1x, port-based network access control. Zero Trust focuses on protecting resources and not necessarily network segments or locations, subnets, and VLANs. From a management standpoint, you want to implement a Zero Trust architecture. Now, there are some variables here. So, for example, on the left-hand side, we have identities. Those are actually going to be individual users, applications, and services. So we'll have an identity provider, and that would be something like Active Directory, Open LDAP, Kerberos. It could even be a cloud service provider like Amazon Web Services, Google Cloud Platform, or Microsoft Azure. And we'll be using permissions and roles, identity and access management, multi-factor authentication, those types of tools that tie into user and session risk management. Below that, to the left, are the devices, corporate devices and unmanaged devices. And these can have agents installed, or they could be agentless. If it's an unmanaged device, we could use something like our security policy enforcement or .1x to place that device into a restricted zone or VLAN, go through device inventory, and then perform remediation. Regardless, this is all managed through a centralized security policy enforcement tool that, of course, does real-time policy evaluation, but also is going to have threat intelligence and threat modeling, often with the cloud or a software as a service provider, giving us visibility and ongoing analytics, and, as much as possible, automating the process and orchestrating all the tasks. If we look to the right, we can see that we have a full implementation solution which involves data, apps, infrastructure, and network. So full implementation would apply the Zero Trust architecture to all of those elements, or we could do a point solution that just focuses on, for example, software as a service apps and on-premises apps, possibly using a cloud access security broker. Or we could just focus on infrastructure. We'll classify, we'll label, we'll encrypt, and we'll use our threat intelligence to give us adaptive access, often using attribute-based access control, advanced solutions for access control that can be applied to our MAC model or our DAC model or our role-based model to be adaptive based on different variables and different characteristics and attributes of the identity or the subject or the user. As mentioned, Zero Trust is an ongoing, evolving infrastructure, and there are quite a few vendors that offer solutions to integrate this into a wide variety of different enterprises and organizations across many different business sectors. In this lesson, we're going to look at secure defaults or security by default, and we'll describe this by comparing it to some other types of SDLC methodologies or software development lifecycle approaches. One would be secure by design. With secure by design, the program or application is developed with security integrated into the entire software development lifecycle, SDLC. We often call this DevSecOps. Another method is secure by deployment. In this example, the application or the system is deployed into an environment where security is highly considered in the network and system design. And then we have secure by default. This design consideration assumes that the application is natively secure without any modifications or extra controls. It's gone through a large amount of testing, and even somebody with white or gray box knowledge shouldn't be able to penetrate the security. Now, of these three, secure by deployment would be the least secure. Security by obscurity, which means basically hiding things or making the code complex, is less secure than all three of these methods. With secure defaults, the existing default configuration settings should be the most secure possible. So again, we can be talking about systems, we can be talking about software. Secure defaults can often be delivered using infrastructure as code. In other words, pre-tested stacks, often in YAML or JSON format. A single source of truth built on secure defaults. You can use tools like Terraform or AWS CloudFormation to accomplish this. Keep in mind, however, there's some downside to secure defaults. Often, you can lose productivity or create a less user-friendly environment. You have to find that delicate balance. Secure defaults can be native to the platform, or they can be policy-based. And they can involve other principles, such as compartmentalization and mediated access through a proxy. A real-world example would be Microsoft Azure's secure defaults. For instance, they require all users at Azure to register for Azure Active Directory multi-factor authentication, require administrators to perform multi-factor authentication, MFA, block legacy authentication protocol, require users to perform multi-factor authentication when necessary, and protect privileged activities, such as access to the Azure portal. Let's talk about the concept of fail or failing securely. This involves the implementation of a mode of system termination functions that prevents loss of the secure state when a failure occurs or is detected in the system or application. We see this in systems that have a state machine, a trusted state machine, for example, like SE Linux or TPM, Trusted Platform Module. The failure still might cause damage to some system resource or system entity, but it doesn't create a vulnerability. To fail securely means to implement secure defaults to deny access, deploy failure undo changes or rollbacks to a secure state. We also call this secure fallback. Failing securely involves check return values and conditional code or filters for failure defaults, and to make sure that even with a loss of availability, confidentiality, and integrity still remain. A real-world example would be fail open versus fail closed firewalls. Keep in mind this could also apply to other security appliances as well as intrusion prevention sensors or secure logging. Fail open means if there's a component failure or a system crash of a firewall or an IPS sensor, the traffic is still allowed to flow from the ingress interface to the egress interface in order to prevent inconvenience to users or productivity of data flows. This is a less secure option, and again, it can apply to a wide variety of devices, for example, to NetFlow collectors, or syslog servers, or SIEM systems. Fail closed means if there's a component failure or system crash of a firewall or sensor, the traffic is not allowed to flow from the ingress interface to the egress interface in order to prevent an attacker from launching an exploit by forcing a failure. To enforce this, we typically apply administrative or managerial controls, which means it's part of a policy, a written security policy, as well as technical controls. In other words, a setting on the security device, the appliance, the SNMP agent, or firewall or sensor. In this lesson, we're going to explore the concept of privacy by design, and we're going to use the NIST privacy framework as our prototype. Individuals, particularly end users who are untrained, do not always understand the possible consequences for their privacy when they interact with applications, systems, products, and services. This is especially true when using endpoint devices and mobile devices. Failure to design for privacy can have a direct negative effect at both the individual and societal levels, affecting an organization's brands, in other words, their value proposition of a product or service, the financial bottom line of the organization, and future prospects for growth. The primary and secondary loss due to privacy breaches can be overwhelming, and often the secondary loss, for example, future prospects for growth, or increased cost for borrowing money from lenders, can have a cascading effect, making secondary losses often more than primary losses. For the CISSP course, I want you to be aware of the NIST privacy framework. The NIST privacy framework is a tool for improving privacy through enterprise risk management, and it's on version 1 as of this recording. It's a voluntary toolkit developed in partnership with various industry stakeholders. The vision of the privacy framework is to assist organizations in identifying and managing their privacy risk, and the goal is to protect individual privacy. It also helps to build innovative products and services with integrated privacy features. To accomplish privacy by design, using the NIST privacy framework, you're taking privacy into account as you design and deploy systems, products, and services that affect individuals. You're communicating about your organizational privacy practices with all of your stakeholders. You're realizing that privacy issues can be different when dealing with other countries and jurisdictions. For example, General Data Protection Regulation, or GDPR, when operating within the EU or dealing with the EU. Encouraging cross-organizational workforce collaboration by developing profiles, choosing tiers, and the achievement of outcomes. There are 3 elements to the NIST privacy framework. The framework core provides an increasingly granular set of activities and outcomes that enable an organizational dialogue about managing privacy risk. Profiles are a selection of specific functions, categories, and subcategories from the core that an organization has prioritized to help it manage privacy risk. For example, database privacy could be a category, and one of the activities could be to use abstraction or tokenization to represent the underlying data. Implementation tiers support communication about whether an organization has sufficient processes and resources in place to manage privacy risk and achieve its target profile. In this final short video of this course, we'll look at the concept of trust but verify. Trust but verify is not a zero-trust approach to security. However, it does introduce stronger identification mechanisms. To fulfill a multi-factor authentication, MFA, something you have prerequisite, we continue to deploy physical tokens that generate different one-time passwords, OTPs, every 60 seconds, or, with mobile phones, using OTPs being sent as text messages. However, mobile malware can intercept these messages and forward them to fraudsters. This rising threat has driven NIST and others to recommend moving away from SMS-based OTPs. The advanced verification comes in the form of more stringent multi-factors, such as biometric authentication. Vendors often identity and access management solutions with identity analysis for attribute-based access control, or ABAC. Trust but verify may eventually lead to expanded usage of user behavioral analytics, UBA, and artificial intelligence to enhance and improve the trust but verify model in certain environments. In this course on secure design principles, you learned about least privilege and defense in depth, separation of duties and zero trust, fail securely and secure defaults, and the concepts of privacy by design and trust but verify. In the next course, you'll learn about organizational roles, responsibilities, and processes, due care and due diligence, and compliance, legal, and regulatory issues. Let's begin this course looking at a very important principle that all security practitioners, engineers, architects, and developers must understand, and that is, you must align security with the needs and the goals of your business. Now, if it's a nonprofit or some other organization like an agency or government, we'll just call it an organization. Regardless, there is a value proposition, and a security practitioner must align all of the security functions to a business's strategy or to the organization's value proposition, whether they're a product or a service, profit or nonprofit, public or private, to the organization's charters, to their goals, to their missions, and their objectives. Every security initiative must be coupled and aligned and have synergy with the strategic and tactical goals of the enterprise. Now, this alignment must permeate through all of the organizational processes. This includes top-level governance. It could be steering committee charters or publications, any corporate initiatives, to name a few. Security must also permeate through all IT service management initiatives like change and configuration management, availability management, and so on. Security strategists must account for any major changes to organizational operations or activities. That can be due to a wide variety of factors, but for example, an upcoming merger or acquisition, or a sudden provisioning or deprovisioning due to some event. Security must react to changes. Mergers are a deal to join two existing companies into one new ongoing enterprise. That will greatly affect your security initiatives. It could be a divestiture or a demerger. This will involve cleaning up access rights, normalizing identity information, and of course, data loss prevention as you engage in the divestiture process. There may be legal ramifications. For example, during an acquisition or a merger, there may be a dark period that has to be enforced, and it may be the job of the security practitioners or administrators to make sure that security and privacy is maintained and that data is not lost or leaked. Other reactions would be dealing with privacy issues, data sharing throughout the change of the business model, interconnection agreements that may be set up or terminated. These are all often involved when there's a change to your business operations. Another aspect of aligning security to business or to your organizational enterprise is to understand all of the internal influences you have to consider. Is your organization functional? In other words, a top-down traditional organization, where your departments and business units are based on functions. For example, the finance department, the marketing department, the sales department, or is it a more flatter, projectized organization where individuals who may have a job title will actually work horizontally across different projects and programs? That will affect, for example, the way that you implement security, for example, single sign-on and federation. Who are the members of executive management, your C-suite or your C-team? Which of those team members do you answer directly to, or which of those team members does your direct supervisor answer to? You have to be aware of the needs of stakeholders, both positive and negative stakeholders, and the internal consumers of the resources and services that you offer, let's say, through your service desk. Internal customers would be your own departments and business units and organizational units. You have to understand the management structure. Do you have a good idea of your organizational chart in your organization, not just your department? Do you have internal auditors? Do they do auditing on a regular basis? Or on an ad hoc basis, or both? Are you an auditor? And do you understand the internal key value propositions? What value do your users and your employees get from the company, and vice versa? Do the employees of your company understand their role and their responsibility in creating a more secure and private environment? And of course, there's external influences. Now, as a security practitioner, you're more likely to deal with the internal influences on a day-to-day basis, but there may be some situations where you will deal with external influences. Typically not stockholders, bondholders, and partners, unless you're setting up secure channels for strategic partners, or providing security at a stockholder or bondholder meeting, dealing with regulators. Supply chains and vendors are important external influences, and your role as a security engineer in securing the supply chain and your relationship with vendors and those channels is critical. Your customers and your clients are external influences. Your lenders and any socio-political or economic factor can be an important external influence that can affect how you implement security. For example, a global pandemic. We might assume that understanding the organizational roles and responsibilities and processes is part of the human resources department, or maybe some other management. However, security initiatives require a broad awareness of all organizational roles and responsibilities, and this really ties into identity and access management, placing the right people in the right groups or the right containers with the correct rights and permissions, just for starters. Companies are organized in different ways. Some are traditional top-down organizations, functional organizations. Some are more flat, horizontal organizations that are projectized. Or many organizations do a lot of outsourcing. They may be on-premise. They may be in the cloud. They may have a large number of remote workers and teleworkers due to unforeseen circumstances. As I mentioned, directory services like Active Directory, eDirectory, and Open LDAP, as well as cloud service provider directories, are often closely aligned and mapped to organizational duties and job titles. Roles and responsibilities will often directly affect access control methodologies and sensitivity levels for mandatory access control architectures, MAC. Responsibilities can also drive our role-based or attribute-based access control models. RBAC and ABAC access decisions typically rely on organizational charts, roles, responsibilities, or locations in a user base. The role is often set based on evaluating the essential objectives and architecture of the enterprise, aligned with the subject's job title and responsibilities. The security practitioner must be aware of these details. We must also be aware of who owns data and who owns assets in the organization. Let's start with the owners. Owners are often the creators of the object or the data, especially in a discretionary access control model. Data or asset owners often determine the classification level. They'll decide on handling and tagging or labels of the asset or the data. While I'm here, let me also mention data processors. On the exam, the processor may be a separate category of data ownership. Now, typically a processor has zero ownership. They just do data input in a command line interface or a console or some type of graphical interface console. They're just simply there to input data into a spreadsheet or a database. We call them data processors. Next, we have data stewards. Data stewards manage assets from a business perspective. Stewards often deal directly with customers, internal customers, and external customers. And stewards often ensure compliance with standards, and administrative or managerial controls, as well as data or asset quality. Imagine you were a guest on a luxury yacht. The stewards are often the ones dealing directly with the guests or the customers. Then we have the custodians. Custodians maintain the assets from a technical perspective. So, going back to our luxury yacht analogy, this would be the first mate, the second mate, and the third mate, the ones working on top of the deck, dealing with the yacht from a technical perspective. Custodians may also deal directly with stakeholders and management. Custodians ensure confidentiality, integrity, authenticity, and availability of data and assets. Finally, we have officers. This is where the buck stops. Officers are often a higher level than owner. These would be Chief Information Officers, CIO, Chief Privacy Officers, CPO, and Chief Information Security Officers, CISO. This is executive management, and they're the ones ultimately responsible for how data and assets are handled in the organization. More often than not, data and asset owners will answer to one of these officers directly or to a supervisor who answers to an officer directly. Regardless, it's important for the security practitioner to be aware of who owns, who's a steward, who's a custodian, who processes data and assets, and who are the officers in the organization and their roles and responsibilities. In this lesson, we're going to talk about governance, but before we do that, let's define a couple of terms. First, due diligence. Due diligence relates to the act of performing thorough research, thorough information gathering, planning before committing to a particular plan of action. It involves proper information gathering, planning, testing, and strategizing before development, production, and deployment. So, for example, from a human resources and security standpoint, it would be due diligence to perform comprehensive background checks before hiring, or additional background checks before promoting somebody to a higher position. Due diligence could involve investigating a cloud service provider thoroughly before signing a Memorandum of Understanding, MOU, or MOA, Memorandum of Action. It could involve testing and evaluating non-repudiation techniques such as digital signatures and digital certificates before signing contracts or developing code. Due diligence often involves understanding which framework is required by law or is applicable under the vendor due diligence. For example, how federal agencies adhere to security mandates when controlled unclassified information, CUI, must reside in a non-federal system and organization. Due diligence can also relate to supply chain security as well. Due care is something different. Due care refers to the degree of attention that a reasonable person takes for a particular entity. For example, an enterprise mobility management initiative. It's the level of judgment, attention, and activity that a person would engage in under similar circumstances. Due care refers to ongoing activities after the due diligence has been performed. Some due care activities would be performing the necessary maintenance and patch management to keep a system or application available and secure. It could be taking all the necessary precautions to ensure that an IP packet arrives with confidentiality, integrity, and availability, CIA, properly applied using various technical controls. Due care can involve using security principles like least privilege, defense in depth, separation of duties, zero trust, and more for continual improvement and maturity. Due care and due diligence is all a part of governance. The need for governance exists anytime a group of people comes together to accomplish an end or a goal. Governance typically focuses on three attributes or characteristics. 1. Authority. There is typically a chain of command that delivers governance, often a board of directors, executive management, C-suites and C-teams, or other types of officers. Governance involves decision-making, top-level, macro decision-making, and accountability. Governance is focused on the structure and processes for sound decision-making, accountability, management, and conduct at the top of an organization. These decisions will flow down into other subsets of governance. For example, security governance, supply chain management, technical and strategic governance. It directs how an organization's objectives are determined and achieved, how risk is controlled and addressed, and how the delivery of value is improved on an ongoing basis. A subset of global governance or corporate governance is security governance. This is broadly defined as the rules that protect the assets and continuity of an organization. Security governance can include mission statements, charters, declarations of value propositions, policies, standards, best practices, and procedures. Security governance guides the course and control of organizational security operations, initiatives, and activities, often the result of a security steering committee or security team or group In the Security Operations Center, or SOC, the security practitioner's strategy will be derived from this effective security governance. Some security governance activities would be creating a risk register, or a risk ledger or log, or populating the risk register on an ongoing basis, publishing in a written format or to an intranet website all compliance and regulatory requirements, tracking and recording all compliance and remediation initiatives, aligning security strategy with the organizational goals, most often through a written security policy, performing vital roles in risk assessment and risk management, and documenting stakeholder interactions and reporting related workflows. In the previous lesson, we looked at governance, and we looked at security governance, due diligence, due care. Now we're going to look at a component of governance known as compliance, along with other requirements, for example, privacy, protecting data, intellectual property, and those types of issues. Now, compliance is defined as observing a rule, such as a policy, standard, specification, or law. Regulatory compliance, which is different than just organizational compliance, actually outlines the goals organizations want to accomplish to certify or be accredited that they understand and take actions to comply with certain policies, government regulations, laws, and other relevant issues. For example, companies that provide products and services to the United States federal government must meet certain security directives set by the National Institute of Standards and Technology, or NIST. Specifically, NIST Special Publication 800-53 and SP 800-171 are two common mandates with which companies working within the federal supply chain may need to apply. Security governance and security compliance is often responsible for publishing all compliance and regulatory requirements for the organization. All personnel compliance and remediation initiatives should be tracked and recorded in a compliance database. This could be the risk register or risk log in a small to medium-sized organization. In a larger organization, it'll be a larger database, often under the umbrella of the Chief Privacy Officer, the CPO. There should be guidelines for using special compliance scanners for finding user vulnerabilities. And again, only certain authorized individuals should use those compliance scanning tools. The risk register or ledger can also be used to help fulfill compliance policy requirements, as mentioned. Some requirements of privacy policy are to describe controls to protect intellectual property, IP, personally identifiable information, PII, personal health information, PHI, and other sensitive data from data leakage, data loss, and data breach. Privacy policy is often needed to assure adherence to regulations such as the Computer Fraud and Abuse Act, Electronic Communications Privacy Act, and the Identity Theft and Assumption Deterrence Act, specifically in the United States. In the EU, for example, for the avoidance of penalties from the GDPR, you should realize the first violation is up to 10 million euros, or 2% of the company's global annual turnover of the previous financial year, whichever is higher. The second violation has a penalty of up to 20 million euros, or 4% of the company's global annual turnover of the previous financial year, whichever is higher. The bottom line, violating privacy policies, especially when it's governance and regulations from the government, can be quite costly. Privacy protection is often mandated in regulations or industry compliance beyond GDPR with standards in the U.S. like HIPAA or PCI DSS. HIPAA for the healthcare and medical field, PCI DSS for credit cards and bank cards. You need to identify all data owners and processors. You need to discover incidents of data remnants. In other words, physical attributes or artifacts of data that can remain on a storage device. You must implement limitations on data collection and have a policy that allows collected PII and PHI to be scrubbed before sharing with a research institute or, for example, the healthcare community cloud. Data privacy also involves including data loss prevention DLP engines, for example, the RSA DLP engine in a Cisco email security appliance. Let's talk intellectual property. The global shift towards service-oriented enterprises has enlarged the role of intangible assets and intellectual property. The need for protection and control of data loss and leakage has increased drastically. Intellectual property can be elements such as copyrights and trademarks, patents and formulas, corporate trade secrets, and upcoming marketing campaigns for new products or emerging products or services, digital rights and licenses, and cryptographic keys and passwords. There are consequences to privacy breaches and data breaches. We typically break these up into primary and secondary loss. Primary loss would be the productivity lost in incident handling or incident response to a data breach. The response of your swarm team or your incident response team as they drop their normal duties and deal with the event or the incident or potential disaster. Replacement of parts, data from restoration mechanisms, or replacement of employees who have been terminated due to data theft or data breach. Those are common primary losses. Secondary losses, however, can be larger because they can be cascading losses in terms of fines and judgments, losing competitive advantage, and a hit to your reputation. Those things can also lead to higher lending costs or the loss of partners or vendors or even customers. Some organizations, due to the type of content that they're involved with, will have digital rights management or DRM. This is access control technology that protects licensed digital intellectual property. DRM is used by publishers, manufacturers, and IP owners for digital content and device monitoring. Digital media licenses attempt to balance the rights of IP owners and Internet users by protecting rights and profits for digital product manufacturers and retailers. Think of Netflix, Hulu, and Spotify. DRM protects copyrighted digital music files, apps, software programs, films, TV shows, games, and other media. We'll also see blockchain NFT, non-fungible tokens, introduced to help protect digital rights moving forward. Here's an example of DRM for Adobe PDF files. In other words, applications and tools that deny authorized sharing, tools that watermark the PDF files, track document usage, enforce expiration, and integrate with e-commerce solutions. You can even restrict these PDFs to specific IP CIDR ranges, or revoke access based on a least privilege principle. Another initiative to get privacy is data minimization. This is a directive that states that collected and processed data should not be used or kept unless it's critical to operations. The details should be determined early in the life cycle to support data privacy standards such as GDPR for the EU and organizations doing business with the EU. You can also employ tokenization to enhance privacy. Data tokenization is a technique used to remove directly identifying elements from the underlying data. The process replaces the raw data with randomly generated tokens or pseudonyms. It is most often deployed with structured data like card numbers, credit card numbers, and national identifying numbers like the Social Security number SSN used in the United States. In order to comply, the original data does not leave the enterprise, even to a cloud service provider. Also, tokenization can be combined with encryption to achieve further defense in depth. In order to implement data privacy, data loss prevention, and other compliance issues will rely heavily on security control frameworks, such as the ISO IEC 27000, a very broad, flexible, and mature framework focused on information security. It's the security equivalent of the more widely known ISO 9000 quality standards for manufacturers. You may use NIST SP 800-53 Revision 4. This has evolved over 20 years and can be seen as the father figure for other security control frameworks. It's mature and comprehensive and can be aligned to other ISO standards such as ISO 9000 quality management. It's very good for large businesses, as well as those with a U.S. connection. You may use COBIT 5 from ISACA. This is Control Objectives for Information and Related Technology, and it was created by the Information Systems Audit and Control Association. It's a framework and a supporting tool set that allows managers to bridge the gap between control requirements, technical issues, and business risks. Internationally, you may use AGATE, Atelier de Gestion de l'Architecture des Systèmes d'Information et de Communication, a framework for modeling computer or communication systems architecture. There's IDABC, Interoperable Delivery of European e-government services to business administrations, businesses, and citizens. It's an EU program launched in 2004 that promoted the correct use of information and communications technologies, ICT, for cross-border services in Europe. There's Obashi. Obashi provides a method for capturing, illustrating, and modeling the relationships, dependencies, and data flows between businesses and information technology assets and resources in a business context. Generally speaking, organizations will face cyber threats in three main areas. First is disruption. This is where cyber criminals will use new ransomware, for example, to seize the IoT, Internet of Things, new types of devices and components and appliances that are recently on the Internet. Then distortion, the spread of misinformation using bots, distributed denial of service attacks, and other automated sources to cause a compromise of trust. And deterioration. For example, advances in smart technology will negatively impact an enterprise's ability to control their information. Other emerging cybercrime issues include artificial intelligence AI-enhanced adaptive malicious software, AI fuzzing to start, automate, and accelerate zero-day attacks, machine learning poisoning Trojans and backdoor malware, hacking of smart contracts based on buggy or unsecured deployment, and vulnerabilities of cloud computing. This data is from a report from 2019, and it's still valid today, and it will still be for the next few years. It's from Oracle and KPMG, their Cloud Threat Report. The question was, what are the biggest cybersecurity challenges currently experienced by your organization today? The largest percentage, at 33%, was detecting and reacting to security incidents in the cloud. Coming in second, at 29%, lack of skills and qualified staff. And that's why you're here as a CISSP candidate, because we need more qualified security professionals. From the same report, this question asks, which of the following represents the biggest cloud security challenges for your organization? Coming in at almost 40% was maintaining secure configurations for our cloud resident workloads. The next three responses are equally pertinent. Satisfying our security team that our public cloud infrastructure is secure, maintaining strong and consistent security across our own data center and public cloud environments in use, and cloud-related security event management challenges. The most common cyber attacks used to externally perform data breaches are ransomware, malware variants, phishing, and denial of service DDoS botnets. The most common internal threat is the personally compromised privileged insider. Data breaches have become more widespread primarily due to cloud computing and the increased usage of digital storage. For example, social media breaches accounted for 56% of data breaches in the first half of 2018, according to IT Web. Over the last 10 or more years, there have been 300 data breaches involving the theft of 100,000 or more records, according to Forbes. The U.S. had 1,244 breaches in 2018 and 446.5 million exposed records, according to Statista. Data breaches exposed 4.1 billion records in the first 6 months of 2019, according to Forbes. And as of 2019, cyber attacks are considered among the top 5 risks to global stability, according to the World Economic Forum. Bottom line, regardless of what year this is now, when you're taking this training, these numbers are only going up. We also have to contend with licensing issues. Security professionals must be familiar with the issues involving software licensing and agreements. For example, there's contractual license agreements. These are traditional, written contracts and contracts that are digitally signed. There's the shrink wrap license agreement. These are the ones that are written on the packaging. For example, the software packages that you buy at a brick-and-mortar retailer or an online retailer. There's click-through license agreements. These are very common. These are the ones we click through during install, either off of a digital drive or off the internet. And there's cloud service provider license agreements as well. This, of course, depends on the managed service, infrastructure as service, software as service, or platform as service. If your organization deals with import and export of hardware and software, as a security practitioner, you may have to contend with import and export issues. In the U.S., these mandates began during the Cold War to control trans-border flows. For example, the International Traffic in Arms Regulations, ITAR, control the export of items that are specifically designated as military and defense items. The Export Administration Regulations, EAR, cover a broader set of items, and your organization may be subject to these regulations. In addition, supply chain security is critical when you're engaged in import-export activities. Cybersecurity-related trade conflict is an emerging global phenomenon. Countries can do nothing, or they can develop import trade barriers, or they can restrict procurement, or they can develop norms, or they can escalate the conflict. Those are their 5 main options. Companies within those countries can make recommendations. They can comply, they can avoid, they can collaborate, or they can compromise based on the situation. When it comes to import and export issues, encryption export controls are a key issue that the security practitioner should be aware of from a management standpoint. And again, on the CISSP exam, a lot of these issues and topics are from an IT management standpoint. For example, the Department of Commerce's Bureau of Industry and Security sets forth regulations on the export of encryption products outside the United States. There's also the issue of trans-border data and information flow. Consideration should always include the flow of data and information and goods across international borders and all legal and regulatory implications. These issues can change rapidly based on various geopolitical factors. Security initiatives must also consider variances in cultural norms, customs, sensitivities, and behaviors. For example, customs that differ between the European Union and APAC. Policies, controls, and procedures can differ based on region. Countries are typically under different regulations and mandates. You have to be aware of those when you're dealing with other countries. We can rely upon security architectures like AGATE, IDABC, OBASHI, ITIL, ISO, or TOGAF. As mentioned, the Department of Commerce's Bureau of Industry and Security, BIS, controls non-military cryptographic exports, and you may have to deal with them. Cloud computing is transcending traditional boundaries and jurisdictional barriers as well, and introducing a wide variety of new challenges. Well, here's a topic that probably belongs in the next course when we look at dealing with personnel issues and employment issues. However, dealing with investigations from a security standpoint can often go beyond just working with HR or in the hiring practices. So let's look at some reasons why security practitioners would engage in investigations. First, as I mentioned, you have employment candidates. So they go through screening processes and hiring processes. And often, as we'll see here in a moment, they can go through elaborate investigations and background checks depending upon the sensitivity of their job role and responsibility. If somebody works for the government or for a particular agency and they get promoted to a higher sensitivity level, let's say, for example, from secret to top secret, or they get a promotion, they may have to go through additional background checks, possibly more stringent background checks. Also, different organizations will do periodic investigations or periodic reviews as part of their employment policy. So, for example, certain investigations done in the military or in government agencies may be done every 1 to 3 to 5 years, regardless of promotion or job role or responsibility. The security practitioner may have to do investigations as part of compliance or auditing or privacy policy issues. And the investigation may be part of incident response. If you're a member of the incident response team or an IRT swarm team who joins others for a particular event or incident, you may be involved in investigations. Or if you have forensic skills, you'll be involved in cyber forensic investigations. In the United States, we have the National Background Investigation Bureau now, NBIB. This used to be called the OPM. You can see there at the bottom, but now it's the NBIB. And here you can see an example of some investigations you would go through for a government agency job or a government agency promotion. We start out reviewing and scheduling the investigation, and then typically we'll do inquiries. The inquiries involve phone calls, email, maybe even sending out letters or surveys to employers, schools, law enforcement, and all of the references they put on their resume. Then there'll be automated national agency checks with the OPM, the Office of Professional Management, the FBI, the Federal Bureau of Investigation, the CIA, the Central Intelligence Agency, the State Department, the INS. I think we call that the USCIS now, the U.S. Citizenship and Immigration Services, Credit Bureau, for example, and maybe even the IRS. And then you have field work, and that involves actually going out and doing personal interviews in person, meeting with previous employers, previous schools, administrators, law enforcement, and personally following up on references. Then the investigation is reviewed, and then possibly it's an iterative process. You go back and do additional investigation. Once you're satisfied, the investigation is closed and documented, and the results are sent in a report to the parties that are involved, the employer, the agency, whoever. In this course on security governance principles, you learned how to align security with business roles and responsibilities. You learned about governance, due care, and due diligence. We discussed a wide variety of compliance, legal, regulatory, as well as import-export issues, and investigations for the purposes of security. In the next course, you'll learn about policy development and implementation, working with vendors, consultants, and contractors, and security awareness, education, and training. In this first lesson, we're going to explore policy development and implementation. Policies, specifically security policies, establish a general framework within which to work and a guiding direction to take in the future. The function of a policy is to classify guiding principles, direct behavior, and offer stakeholder guidance and a security control implementation roadmap, administrative, technical, and physical controls. An information security policy is a directive that outlines how an enterprise plans on protecting its data, applications, and systems. In other words, how are we going to achieve confidentiality, integrity, availability, authenticity, possession, control, and utility? It helps ensure compliance with legal and regulatory requirements, as well as preserve an environment that sustains security principles. Policy documents are high-level overview publications, either in written format or published to an intranet, that guide the way in which various controls and initiatives are implemented. When you develop your information security policy, it should have 6 elements. First, it needs to be sanctioned. The policy must have the support of executive management, or the C-suite or C-team. This means visible participation and ongoing action, communication, and even campaigning to achieve the level of investment and prioritization that you need. Next, it needs to be applicable to the organization. So, from a strategic standpoint, the information security policy has to support the guiding principles, the mission, the charter, the goals of the organization. Tactically speaking, it has to be relevant to those who must comply to the policy. It should be realistic. Can it be successfully implemented? The policies need to reflect the reality of the environment in which they're going to be deployed. Information security policies and procedures should only ask for what is attainable. If we're assuming the policy objective is to advance the guiding principles of the enterprise, then we want to assume a positive outcome. We're not going to set up our constituents for failure. It should be flexible. The policy should be able to accommodate change and be adapted as necessary. An adaptable information security policy will recognize that security is not static. It's not a one-time, point-in-time endeavor. Instead, it's an ongoing, continual improvement process to support the organizational mission. An information security policy needs to be comprehensive. The policy scope must include all of the relevant parties, all the business units, all the stakeholders, all of the entities. It must be inclusive. It needs to take into account the objectives of your organization, regulations, international laws, cultural norms of your employees, your vendors, your suppliers, your business partners, obviously your customers, but also things like environmental impacts and socio-political phenomenon. And of course, don't forget the shareholders if you have them. It needs to be enforced. It needs to be statutory. So enforceable means that the administrative, physical, or technical controls can be put into place to support the policy, and yet you have the appropriate sanctions in place if someone does not adhere to the policy. And typically there's several levels, from a verbal warning to termination, hopefully several stages in between. But the bottom line, the information security policy should be sanctioned, applicable, realistic, flexible, comprehensive, and enforced. Policies can change, and they will change based on new technologies. For example, you may have a Internet of Things hardware authentication policy. This is new technology, authentication at the hardware and firmware level for IoT. New policies for user behavioral analytics that we apply to our end users, often analyzed with AI and machine learning. So you're going to have policies for deep learning and machine learning and artificial intelligence. That could include virtual reality and augmented reality through your endpoint devices. New policies for interacting with cloud providers, relating specifically to that shared responsibility model between you as a consumer and your provider. Infrastructure, platform, software as a service. And with rapid changes to mobility, such as 5G and WPA3, you'll have organic and dynamic enterprise mobility management policies. In the next lesson, we'll talk more about the subsets of policies things like standards, guidelines, processes, and procedures. Let's begin this lesson talking about standards. Standards allow an information technology staff to be consistent and systematic. Standards specify the use of specific technologies in a uniform way because no one individual practitioner can know everything. Standards also help to provide consistency in the enterprise because it's unreasonable to support multiple versions of hardware and software unless necessary. Standards are usually mandatory, and the most successful IT organizations have mandatory standards in order to improve efficiency and to help keep things as simple as possible. Remember that security principle, keep it simple. Guidelines, however, provide a list of suggestions on how one can do things more effectively. Guidelines are similar to standards, however, they're more flexible and they're not typically mandatory. They're used to define how standards should be developed or to guarantee some level of adherence to general security policies. Some of the best guidelines available are in repositories known as best practices. For example, the NIST Computer Security Resource Center, the NSA Security Configuration Guide, the Center for Internet Security CIS Top 20. Below that, we have procedures, also referred to as processes and practices. Procedures are usually required, although they're the lowest level of the policy chain. Procedure documents are longer and more detailed than standards and guidelines documents. Procedure documents include implementation details, usually with step-by-step instructions and graphics, topological maps, flowcharts, the types of media you would see at a site such as Lucidchart. Procedure documents are extremely important for helping large organizations achieve the consistency of deployment necessary for a secure environment. Procedures, processes, and practices are often deployed using infrastructure as code in YAML or JSON format, using tools such as Terraform or Amazon Web Services CloudFormation. Remember, procedures are also known as practices. We also hear procedures referred to as SOPs, Standard Operating Procedures. These are step-by-step instructions that define how workers carry out routine tasks. SOPs can greatly improve efficiency, quality, performance, communication, and compliance with regulations. Often, SOPs can best be delivered using automation and orchestration tools. Some considerations for standard operating procedures would be: describe the purpose and limits of the procedures. Offer all of the steps needed to complete the process, leaving nothing out. Clarify concepts and terminology. Often, you'll have a glossary. Consider health and safety issues in hardware and physical implementation. And list the location of all necessary supplemental resources necessary to carry out the standard operating procedure. The acceptable use policy is often considered one of the most important sections of a written security policy. The AUP identifies how employees are expected to use resources in the organization. It defines rules of behavior and codes of conduct. For example, using proper and acceptable language, avoiding illegal activities, avoiding disturbing or disrupting of other systems, do not reveal personal information, avoid data leakage or data loss, and do not reveal confidential information. In other words, protect intellectual property, personal health information, and personally identifiable information. An AUP can have several categories. For example, one for mobility and wireless, that's very common. A category for handling operating systems and software. For example, policies that forbid the installation of Type 2 hypervisors like VMware Player or Oracle VirtualBox. the allowing and denying of personal cloud storage, such as Dropbox, the usage of removable media, and can that media be used just inside the facility, or can the media leave and enter the premises? AUPs for email usage, anti-phishing, and web browsing, acceptable use policies that are also controlled with URL filtering and data loss prevention engines, and policies for file sharing or peer-to-peer file sharing sites. Some managerial controls for AUP would be the change management process, having a least privilege policy, enforcing mandatory vacations, enforcing separation of duties, rotation of duties, having a clean desk policy, and social media usage policies. Earlier, I referenced enforcement as being a characteristic of a good IS policy. Several stages of enforcement could involve, first, initial verbal reprimands or warning, then an official written warning, followed up by temporary suspension with or without pay, then termination, and possibly criminal or civil legal action, for example, leading to incarceration, reimbursement, and/or restitution if crimes were committed. In this short lesson, we'll look at some things we talked about briefly in the previous course: the security practitioner's relationship to employment candidate screening and hiring. HR and legal departments must work closely with security policy steering committees and other groups to determine the best practices for screening and hiring. At the start of an interview, for an example, it's not uncommon to sign an NDA, a non-disclosure agreement, otherwise known as a confidentiality agreement. Also, many organizations have employees sign an additional employment contract once they accept the offer. New employees should sign off on all security policies, as well as the acceptable use policy AUP. Activities include working with headhunter organizations and online hiring sites such as Indeed.com. Security practitioners may be involved in confirming some or all of the references. They may assist in approving education, certifications, and especially experience when it comes to security. They may do additional fact-checking of resumes, particularly who are going to have a security role in the organization. Background checks and credit checks may be performed, and all activities must adhere to compliance and privacy requirements. It's not uncommon for a security practitioner, an officer, or an engineer or an architect to conduct technical interviews, especially when hiring somebody in the security department. Technical or phone interviews before the actual on-site interview or meeting. In this lesson, we're going to talk about onboarding. Remember, onboarding is new hire procedures. It's not done until you've actually hired that candidate. It's the process of providing assets, guidance, knowledge, skills, and the behaviors needed or expected for a role or responsibility on a team or in a group. You may provide them videos, printed materials, computer-based training, lectures. There may be formal and informal meetings, and assigned mentors, at least for the first 45 to 90 days. There'll be introductions to other employees, explanation of standards and practices, otherwise known as Standard Operating Procedures, SOPs. This documentation should clearly define all the roles and responsibilities of the onboarded employee. You want to provision all devices, all endpoint devices and equipment, mobile devices, or lay out the bring your own device security policies, pads, laptops, other equipment. You should deliver security awareness through training and acceptable use policy expectations. This should be a written document that the employee who's onboarded will sign. And of course, additional human resources activities. And in the process, be sure to remove any ambiguity and uncertainty. The onboarding process should be concise, clear, and comprehensive. It's very likely that the employee who's onboarded signed a non-disclosure agreement during the interview process. However, there may be additional confidentiality agreements that must be signed by the new hire. An NDA is a legal contract between two or more parties. It's a confidential relationship that is often strictly enforced, especially on the employee side. There can be severe consequences for the employee or ex-employee who violates the non-disclosure agreement. It can be business to business, or it can be business and employee. The NDA identifies confidential information that they wish to share with each other, but not any external parties, and possibly other employees or departments within the company itself, depending upon the sensitivity level of the new hire. For example, if they're hired at a top secret level, the NDA may lay out consequences for exposure to lower sensitivity levels. The information can include intellectual property, trade secrets, technologies, marketing campaigns, ideas, new processes, new products and services, and, if it's military or government agencies, certain types of files that are secret or top secret. The NDA has the goal of restricting the sharing of information with other people and entities. As mentioned, NDAs are commonly used during the interview process, but then introduced again in the onboarding process. A new trend to be aware of on the CISSP exam is automating the onboarding process. Enterprises often deploy systems that involve self-service onboarding of personal devices. The employee registers a new device, and the native supplicant is automatically provisioned for that user and device and installed using a supplicant profile that is pre-configured to connect the device to the corporate network. This is often in a 802.1x PNAC environment using an authentication protocol like EAP-TLS, Protected EAP, or Cisco's EAP Fast. The onboarding process can also be automated using a software as a service provider, often assisted by a cloud access security broker, CISSP. Remember, offboarding is the reverse process of onboarding and can actually involve more security vulnerability than the onboarding process. We'll discuss some of those issues in the upcoming lesson. Let's continue our discussion from the previous lesson and talk about offboarding, or employment termination and transfer best practices. Realize that several of the processes that you'll go through when an employee is terminated or that employee decides to leave on their own will still apply to an employee who is transferred to a different division or business unit, or promoted to a higher position or sensitivity level, or even demoted. So termination and transfer depends upon the circumstances, and there can be a wide array of circumstances. Regardless, we must document all procedures for revoking an outgoing employee or transferred employee access. We must monitor and audit the employee closely in the last hours or days of service, specifically an employee who's leaving the organization. If possible, with human resources departments and possibly legal departments, terminate the employee face-to-face as opposed to using, let's say, video conferencing or a phone call or text. And there should be a witness, an in-person witness, whenever possible. In today's environment, this may not be feasible. However, it's a best-case scenario or best practice. You must meet all regulatory requirements. For example, in the United States, there's a WARN Act, the Worker Adjustment and Retraining Notification Act, that comes into play to protect workers from the impact of the unexpected and sudden loss of employment. Basically, a layoff that is longer than 6 months, or reducing the working hours by 50% in 6 months. There's also Sarbanes-Oxley that can come into play as well, or SOX. There should be a process and policy in place to disable or delete accounts and revoke digital certificates and digital signatures. That revocation of the certificate should also be communicated to the trusted third party. for example, the certificate authority, either the enterprise CA or a third-party CA, so that the certificate revocation list CRL or OCSP database protocol can be used to alert all other parties that are using the public key of that certificate. Accounts may be disabled for a certain period of time, for example 12 months, and then finally deleted. The employee, whether it be termination or transfer, should return all property, all physical and intellectual property. It may be necessary to modify or update any corporate-controlled social media sites. For example, some organizations have a corporate Facebook or other presence that needs to be modified for the terminated or transferred employee. And remember, ex-employees or former employees are near the top of the list of potential threat agents moving forward. So this should be an area of the risk register or ledger or risk log on an ongoing basis. Another important principle of termination and transfer is having the ability to do follow-up interviews, if at all possible. In a follow-up interview, you can often gather a lot of information that's helpful to expose risk and security vulnerability, as the employee who's being transferred or terminated may be more willing to expose weaknesses or vulnerabilities that weren't discovered through assessment or gap analysis. In the exit interview or the release interview, try to identify factors that led to the employee leaving if it was voluntary. How can the organization improve to keep employees if applicable? Discover any potential unknown security vulnerabilities or issues with other employees that haven't been exposed. Remind the exiting employee or transferred employee of their agreements, their NDAs, other agreements and responsibilities. Review the NDA that they signed when they started. Remind the employee of what they're forbidden to discuss with other people and other entities, even as an ex-employee or transferred employee. Always adhere to well-defined offboarding security policies and procedures that should be well documented in the written security policy or published security policy. And collect all corporate assets and property, both physical and logical. Often, if the property is not delivered in a timely manner, there's some process in place to delay final compensation or the final salary payment to that employee until they deliver the equipment or other assets. If necessary, you may need to involve law enforcement to collect the valuable assets. On the exam, it's important to remember different types of agreements and documentation when dealing with third parties. And remember, as a security practitioner, the third party could be internal to the organization, for example, through a service desk, or it could be an external third-party entity. Now, from an external standpoint, we often use what we call service-level agreements, or SLAs. SLAs define the precise responsibilities of the service provider and sets customer expectations. The SLA also clarifies the support system, the help desk, the technical support, the service desk response to problems or outages for an agreed level of service. An SLA can be internal, between business units or departments, as well as external, but usually if it's internal, we're going to call that an OLA, which we'll look at in the next topic. These agreements should be used with new third-party vendors or cloud providers, providing software as a service, infrastructure as a service, and platform as a service for 24-hour support. From a security standpoint, often we're concerned with the cryptographic methods that are used to protect data in transit and data at rest, identity and access management, and privacy issues such as leakage and loss of intellectual property, PHI, PII, and other sensitive information. In other words, in this agreement or our relationship, how do we accomplish confidentiality, integrity, availability, as well as non-repudiation? An OLA documents the pertinent information for regulating the relationship between internal service recipients and an internal IT area or department. That service provider could be a service desk. The difference between an SLA and an OLA is what the service provider is promising the customer versus what the functional IT groups promise to each other in the OLA. An OLA often corresponds to the structure of an SLA from a document standpoint, for example, a lot of similar information, but there'll be some specific differences based on the enterprise and the functional IT groups. Another document is the Memorandum of Understanding, MOU. This is also referred to sometimes as a Memorandum of Agreement, or MOA. Another word for MOU, actually more common, is the Letter of Intent. A formal MOU or MOA usually precedes a more formal agreement or contract. It defines common courses of action and high-level roles and responsibilities in management of a cross-domain connection. Often, it's a commitment to move forward with the contract process with that provider and delivering a high degree of confidence that you're not going to continue the search or seek other providers during that time. It will usually terminate the customer-provider search process so that subsequent time and resources can be dedicated to the next steps or the next phases of a more formal contract process. Another common agreement is the RA, the reciprocal agreement. This is a contract between two organizations that have similar infrastructures and technologies. These agreements are difficult to legally enforce. A common goal is that one can be a recovery site for the other in case of a disaster or a lengthy outage. A reciprocal agreement is a quid pro quo arrangement in which two or more parties agree to share their resources in an emergency or to achieve a common objective. For example, safe media storage of backup tapes and other documentation. So for example, data backup, where you have two departments or organizations that agree to store each other's backup data on their computers. Or disaster planning, whereby each party agrees to allow another to use its site, facilities, resources, etc. after an event or a disaster. An interoperability agreement, IA, is an agreement between two or more entities for collaboration and data exchange. It's often used by sister companies that are both under a holding group or a high-level corporation. It is a binding agreement for sharing information systems, telecommunications, software, and data. An IA, interoperability agreement, is not the same as a reciprocal agreement, RA. An example would be the Interconnection Security Agreement, ISA, that a customer signs for AWS Direct Connect to a service provider or Azure Express Route. As mentioned earlier, these agreements bring into play third parties. Let's look at some other risk factors of dealing with third parties that these agreements are often put in place to protect us from. We have to look at reliability of our vendors and our suppliers, the safety, quality, and security of the supply chain, vulnerabilities with business partners in keeping certain data and information private for the purposes of regulation and governance, the risks of end-of-life EOL products and services where the vendor or the supplier no longer has the particular component or no longer provides support for that EOL product or service, or the posture of the vendor or the supplier for end of service, which had been previously documented in a service level agreement or interconnection agreement or some other type of contract. If you continue to use that product or service, how do you manage the relationship and all of the needs if the product or service is end of life or end of service? Those are prevalent third-party risk factors that security practitioners have to contend with on a weekly basis. In the final lesson of this course, we want to explore security awareness, education, and training. There is a difference between awareness and training and education. Awareness is commonly underutilized. However, if there is an awareness policy or program in place, it can often be overdone. In other words, you overwhelm the employee with information, saturate them with security awareness best practices. However, we can increase awareness by using self-paced, computer-based training modules. The employee can watch videos, go through classroom training. We can also raise awareness by exposing them to posters, newsletter articles, email, and bulletins. Remember, we want to combine the carrot and the stick. In other words, we want to have enforcement when security AUPs and policies are not adhered to, but also some occasional rewards for maintaining a secure environment and buying in to security policy programs and initiatives. We can remind users with system banners, drink cups, mouse pads, notepads, and other media. Training education is more formal. It can be awareness training. However, there'll be more advanced training for sensitive areas or users with elevated roles or higher privilege levels. You should have security training for new hires. Also, technical security training for your IT staff and accelerated advanced training for your security staff, your security practitioners, engineers, administrators, and architects, and specialized training and educational instruction for the C-suite or other executive management or key stakeholders. They should be aware of the organization's mission, charter, and vision from a security standpoint. They need to know all applicable security policies and procedures. Some example security topics in the education and training would be password and badge policy, for example, using their multi-factor authentications, anti-tailgating and piggybacking. In other words, not going into the building or onto a floor or onto an elevator and into an area without using their badge or token, not piggybacking on somebody else's credentials. A clean desk policy at the end of the day, removing everything from the desk, putting it into a locked drawer, locked cabinet, or safe. To raise awareness for email and webmail phishing attacks. Raising awareness and educating employees on different types of social engineering attacks and hoaxing. Training to prevent data loss and data leakage. And an overall education on all relevant governance, regulations, and mandates. The security training should be role-based. In other words, you have your general endpoint users who should go through training and be aware of their AUPs, but you'll also have training for data owners, system owners. Data and system custodians and stewards will go through specialized training. Custodians, a more technical training, where stewards will be more business-related training. Train your administrators and privileged users. Special training for executive users who may not have the deep security knowledge or a more layman's point of view to technology and security. You have executive management, otherwise known as the C-suite or C-team, and even, in some situations, the board of directors can go through role-based security training. Here's an example awareness or education program. First, identify the program scope. What are your goals? And who is the target audience? For example, is it executive management or receptionists? Motivate and get buy-in from employees and management. This is critical. Identify the optimal and affordable training modalities, webinars, classroom training, self-paced computer-based training, and other modalities. And then administer and maintain the Security Awareness and Training Initiative. Finally, evaluate and improve continuously. In this course on security policy, you learned about security policy development and implementation, employment and personnel policies, third-party policies and agreements, and security awareness and training. In the next course, you'll explore data and asset classification, information and asset handling, and data roles and life cycles. Let's begin this course looking at 3 different states of data we need to be aware of because it's going to affect a wide variety of things like risk management, risk assessment, data loss prevention, usage of various crypto systems, a wide variety of administrative, technical, and physical controls. So first we have data at rest. This is what we commonly think of as the information that's stored on hard disks, on workstations and servers, the hard disk drives, the solid state drives, RAID arrays. It's also data on memory cards, SD cards, for example, the data in your data center that you either access over the storage area network or network attached storage. It could be object storage, storage in the cloud, for example, at Amazon Web Servers S3 or Azure Blob. It could be data at rest on archives and backup drives, external and removable drives. Then we have data in transit. Data in transit is also referred to as data in motion, and this is typically data sent either over a wired network like Ethernet or a fiber FIDI ring, for example, or a fiber metropolitan area network. It can also be data sent across the RF spectrum, for example, with wireless 802.11 something. It could be cellular, it could be satellite, data that's in transit. And then we have data in use, and this is volatile data. This would be data in the registers on your central processing unit of your workstation or your devices. This could be volatile data in RAM memory, volatile storage, maybe data that's cached in in-memory only storage like Redis or memcached clusters. Data in use. How do we protect data at rest? Just a quick overview. Of course, we're going to spend the rest of our time in this training for CISSP to look specifically at technical controls, but logically, we're going to rely on conventional perimeter-based defenses. Things like firewalls. Remember, a firewall is a metaphor. It can be software, it can be hardware, it can be a combination. Preventing a fire from spreading from one zone or domain to another. It could be intrusion detection systems, intrusion prevention systems, and things like antivirus, anti-malware. Conventional systems. We can deploy defense in depth access controls or identity and access management to determine who's authentic and who's authorized to access data and what can they do, possibly introducing additional factors like multi-factor authentication before they can access that data at rest. We want to use secure principles. Often with dual operator, it takes more than one person to access some data, or separation of duties, where one particular subject can access parts of data and some other person can access other parts of data or other areas of storage on disk drives or cloud storage. Cryptographic systems are extremely valuable in protecting data at rest. Sometimes it's done automatically. So, for example, if you store an object in a cloud provider, it will be encrypted with Advanced Encryption Standard AES 128 or 256, typically either CBC mode or GCM mode. So we can protect volumes, disks, and individual files at rest. Using software encryption, we can also use full disk encryption FED or move or copy those files over to self-encrypting drives, SED. We can also get protection by partitioning our storage. For example, certain data stored in a secure enclave on a mobile device. Or we can use hardware security modules, SSM, to store cryptographic keys at rest. And these are technologies we'll explore even further throughout the CISSP training. As a security practitioner, you're probably very familiar with protecting data in motion or data in transit. We can do this by using encapsulation methods. For example, a protocol IP in IP can be used. We can have dedicated channels that don't even involve cryptographic mechanisms. You just dedicate leased lines between one site and another, maybe a dedicated fiber connection. More often than not, though, we're going to use crypto systems. For example, SSL TLS, and specifically, when you're going to websites today, you're most likely using TLS 1.1, 1.2, or 1.3, and then higher going forward. IPsec or IP security is a very popular way to create virtual private networks for IP version 4 and IP version 6 at layer 3 of the OSI model. Protecting wireless data in motion. More often than not, we're going to be using WPA2, and more recently, Wi-Fi Protected Access 3, WPA3, and includes some of those new security mechanisms, for example, management frame protection. You can protect data in motion with IEEE 802.1x PNAC, port-based network access control. That's going to be helping us get security at layer 2. Also at layer 2 of the OSI model, 802.11ae MACsec, where we can pretty much get the same type of services that we get at layer 3 packets and datagrams with IPsec, but we can apply those to frames at layer 2, confidentiality, origin authentication, integrity. So these are all a lot of methods we use today to protect data in motion. When it comes to protecting data in use, for example, information that's stored in RAM memory or in caches, let's say Redis caches, this is the least mature protection system. There's a lot of overhead in protecting data in use due to encryption and decryption, and it's costly and difficult to implement. There are some newer methods for protecting volatile data in memory, such as homomorphic encryption. We'll talk about that in an upcoming course. But in a nutshell, you conduct calculations on encrypted data without actually decrypting it. We can also use trusted computing systems to protect data in use, for example, SE Linux. And more recently, we're starting to rely on machine learning and artificial intelligence algorithms and engines, which give us cutting-edge visibility and memory protection. There's a very good reason why we're going to look at data and asset classification here so early on in this course. In the next course, we'll be looking at risk management. And before you can do risk assessment, risk analysis, and risk management, you have to have an understanding of your assets and your data. You need to know what you have to manage your risk. And that involves data and asset classification. And it's quite likely that your organization is using a model, an architecture that has sensitivity levels and classification, possibly in lattices, like a mandatory access control model, such as Bell-LaPadula or BIBA or Clark-Wilson. So you must have a well-established tagging and labeling schema that maps, hopefully, to a configuration management database, a CMDB, such as ServiceNow, or it could be a CMDB in the cloud, let's say Amazon Web Services DynamoDB. We're discovering that NoSQL document-style databases are actually superior than traditional relational database management systems. We want to assess, classify, and label all of our facilities equipment, all of our facilities areas, different buildings, different areas, different rooms, our equipment, all of our physical assets, our data and information assets, human resources or people assets. That's often done in conjunction with a directory service. Don't forget, there's intangible assets or logical assets and intellectual property. And these assets can be on-premises or on-prem. They can be in the cloud or at some other service provider. They may also be at disaster recovery sites. Let's dig deeper into the CMDB. A configuration management database is not a typical data warehouse. It plays a critical role in several IT management initiatives, such as IT service management, ITSM. For example, maybe you're using ITIL 4 or COBIT 5, and IT asset management, or ITAM. CMDBs assist various IT services to help us better align with our business needs by providing current and accurate data for change and patch management, for incident and problem management, for availability management, and release and deployment management. Configuration management practices offer the necessary data we need concerning assets and their configurations, including their interactions and interoperabilities and interdependencies with other assets and other asset classes. This assists administrators and IT managers with problem resolution, with incident response, with network component deployment, and formulating strategy, as well as budgetary forecasting and overall decision making. Let's continue our discussion of information and asset handling requirements. Labeling concerns the classification and prioritization of data, systems, applications, really all assets, to determine the level of protection and how the asset should be handled. Handling controls who has access to the assets and what actions they can take. Handling is based on labeling and how it's been classified. When choosing a classification level for an asset, and this can go beyond data, there are several criteria or attributes that we can use. Now, the most common and the most obvious is value. And if it's valuable, it should be protected. And realize it's not just the financial value, but also the relative value to delivering the value proposition, the service, or the product. Also, it's the value that can be generated or revenue to be generated going forward, not just the present value of the asset. The classification level can be based on architecture. So, for example, the subjects and objects are restricted by a mandatory access control model, or MAC, or possibly a risk-based, attribute-based access control model. The age of the object or the data can be a key factor. For example, over time, the value of assets can diminish. If it's a physical asset, we call that depreciation. However, information and data and files can also depreciate in value over time as well. Over a period of months or years, you may have automatic declassification based on the age of the object. Age is also closely related to useful life. If the information is made obsolete, it can then be declassified or devalued. Useful life can also be the fact that a new version or a new generation of the object has been created, and therefore the previous iteration or version is no longer valuable, or it's lost all of its value. Closely related to architecture is personal association. So if data or a particular subject is personally identifiable, or if it's health information, or if it's at a particular sensitivity level based on its association with personnel who are also at that same level of secret or top secret, it can affect the classification and labeling and handling. In the previous lesson, I mentioned the importance of having a configuration management database made up of configuration items. So typically, we use a key value NoSQL document style database. So for example, we see a schema here that's just one example of many schema you could have. On the exam, what's important is that you do develop a key value pair schema and that it's consistent and that it's comprehensive. So here we can see the person who collected the asset, the name of that person or the data, the source of that asset or that data, the category, which is a tag determined by your entry to the category field. This could also be information coming from, let's say, logging or NetFlow collectors or sensors. You also have the source host, the host name of the particular device or configuration item. So the bottom line is, make sure you have a well-established and comprehensive and consistent schema. In this lesson, let's talk specifically about asset management, and the first takeaway for the exam is this should be automated, bottom line. But asset management involves the tracking of all physical and, if possible, logical assets, tracking them for various characteristics, their location, tracking changes, their disposition, all of this to improve risk management, risk assessment, and possible asset recovery for business continuity activities. Now, whether an asset is real estate or software, or a set of secret keys, the asset manager's main task is to supervise all the activities related to asset management. And this would involve the asset management software, the automated tools that are used, and of course, we're assuming that you have a dedicated asset manager in your organization, although this may be somebody else with a role of server administrator, database administrator, instead of somebody with the title of asset manager. Digital asset manager, however, is a growing enterprise role. For example, managing images, type 2 hypervisors, cryptographic keys, other logical and digital assets and data. Again, automation and orchestration systems are vital, especially for medium to large enterprises. At the heart of asset management is asset inventory control. For a lot of companies whose value proposition is a product, just-in-time is prevalent. But even if your organization doesn't have necessarily a product to sell, you still deal with vendors and wholesalers in a supply chain, and they themselves are also using just-in-time. In other words, they have just enough to deliver to their customers at a given point in time. So we often see backlogs and back orders if there's disruption to the supply chain, for example, like a global pandemic. Managing the inventory and doing it in an automated fashion will help you keep your budget in line. It allows for better security as well, because you are tracking all of your physical and logical assets, and of course efficient management of your operating capital. This may not be your job role, but as a security practitioner, you want to be aware of the fact if your organization is assessing the type of inventory that's being kept. Determine the quantity of goods you must keep on hand. These could be the goods that you're selling to your customers, but they could also be the ones that you're getting from your own vendors. Track the market trends of your competitors. You want to make sure that you have access to the same products and services that your competitors have from various vendors. Identify your minimum stock levels. This ties into your JIT. And again, as I mentioned, this is an inventory strategy used to increase efficiency and decrease waste by acquiring goods only as needed in the production process. And again, this can tie into you who are selling physical products to your customers or your relationship to vendors, and understanding that most of your vendors will be using just-in-time inventory. That can also tie into your disaster response, your disaster recovery as well. There are some best practices for fixed asset inventory software. Realize the scope of your project. In other words, you want inventory to be not necessarily over the entire enterprise, but to break it down in a modular fashion. For example, inventory of your hot spares for your infrastructure devices, your switches, your routers, your firewalls, your multi-layer switches, your sensors, your servers. Assign responsibility for your asset management. If you don't have a dedicated asset manager or digital asset manager, then somebody with a different job title or role will need to take this on. And again, often these are server operators, server administrators, other types of domain administrators. Make sure that all of your qualified personnel are understanding basic fixed asset procedures. And this would involve having some knowledge of accounting systems and inventory systems, not just always relying upon the automation of this, having some ability to work manually if necessary due to an event or a disaster. Obviously, moving forward, we're going to rely on automated software to do this, and look for emerging technological trends. For example, software as a service providers and other service providers that could offer this asset control where everything is being stored in the cloud and we're actually running tools, machine learning processes, and engines from the cloud provider as well. And one of our main goals is to identify and clear out ghost assets, we call ghost IT. You'll also hear this referred to as shadow IT. These could be things like virtualization creep, where you have type 2 hypervisors and ghost software and ghost applications running on workstations and laptops of your end users. Employees using peer-to-peer file sharing to download programs and files that are unauthorized, freeware, shareware, pirated, anti-copyright content. Not only are we creating a baseline for our inventory, but we're also looking for those ghost assets and to remove them from the enterprise. In this short video, we want to identify different roles of the types of people in our organization that will deal specifically with the assets of data. Now, these roles can also apply to other assets as well, but for the sake of the exam, we want to look at these from the standpoint of data. And of course, the first one we have is the data owner. The data owner owns the information, especially in a discretionary access control model. So the owner is typically the person who creates the object. So somebody who creates a file or a folder in Active Directory, or somebody who creates a document library in Microsoft SharePoint. The owner often has the discretion to share or even assign permissions and rights to these objects they create. The owner often determines the tagging and the classification level. They may actually even provide the label itself. They'll fill in the schema. So based on the key, which are already provided, they'll fill in the values. Next, we have stewards. A steward manages the data and often additional metadata. So metadata, of course, is data about data. So it could be files, for example. Say these are files that are stored centrally at a cloud provider. So maybe Amazon Web Services Elastic File System, where a bunch of Linux systems are accessing these files. In this file system, that can grow, up to petabyte levels. They're going to manage this from a business perspective. They'll often be the ones that are going to ensure compliance over where these files are stored, either locally or in the cloud. So based on standards, based on established controls, maybe they're responsible for data quality. Think of the steward in that standpoint. The data custodian is different than the steward. A custodian is the keeper of the information or the data from a more technical perspective. Okay, so not so much from a compliance perspective. The steward is more administrative controls, where the custodian is more technical controls. And so they would be ensuring, for example, the confidentiality, integrity, availability of that data is maintained. You also have data processors. A data processor is not an owner. They have no stewardship. They have no custodial abilities with the data. They're simply there to input into a system, taking raw data and putting it into some type of system so that it can be converted to information. So just basically data entry. They may be involved in, doing batch jobs or other activities, but they have no other relationship with the data other than just simply input, output, and processing. Now, ultimately, the responsibility for data will typically rely on an executive manager, an officer. So the way that data is handled and managed, even beyond ownership, is going to be with a chief information officer or a chief privacy officer or maybe a chief technology officer. So that's basically kind of where the buck stops. But on the exam, make sure that you're aware from a high-level management standpoint, these roles of owner, steward, custodian, processor, and officer. These next two lessons really represent the core, heart and soul of this course, the main information to be retained for the CISSP exam. What we're going to look at here is a particular data lifecycle, and we're going to look at 6 different steps in this lifecycle. And I'm going to go through these and describe these one at a time. These are the 6 phases of data lifecycle according to the CISSP objectives. So you may see various data lifecycles in different training books, different online articles, websites, whatever, but these are the 6 that are on the exam objectives. So make sure that you focus on these, even though you may see these described in other ways, in other materials or other formats. So we have phase 1, collection, phase 2, location, phase 3, maintenance, phase 4, remnants, and then phase 5 and 6 are often kind of a binary, okay? Either you retain it or you destroy it, but we have two separate phases. We decide to retain it, retention, and then phase 6 is destruction, often referred to as disposition, okay? So let's break down this life cycle for the exam. First, we have data collection. This is also called data capture, by the way, and there are three key methods through which data is typically captured or collected. One is data acquisition. This is the consumption of readily available data that has been produced by an entity typically outside of the organization. We're obtaining the data from some external entity. There's data entry. This is the generation of new data values for the organization by human operators or devices that produce data for and within the enterprise. We also call that data input. And then data reception. This is the receiving and the capture of data generated by devices. These can be devices within our organization generating logs or net flow records or other output. This could also be cloud-based through a managed security service provider or a cloud access security broker or some type of system, let's say CloudWatch from Amazon Web Services or Google Cloud Platform services that are operating in the cloud and on-prem. So examples here, SIEM systems, NetFlow collection, logs, also industrial control systems, SCADA systems, basically any information system, and even those that are linked to the IoT, Internet of Things. Continuing data collection. Unless data is collected, it cannot be analyzed. It can't be matched for patterns. It cannot be used for data-driven business decisions. In other words, without the raw data and the collection of raw data, we cannot then derive information. And we need information to give us knowledge and wisdom as part of the maturity life cycle. Now, a key aspect of data collection is that only data necessary for organizational or business needs should be collected. And this is a general data principle, along with things like data abstraction and making sure that there's no direct access to the underlying raw data. Article 25 of the GDPR, the General Data Protection Regulation, by the way, mandates that many companies protect data by design and by default. Enterprises should integrate data protection principles into business activities in the beginning and throughout the entire data lifecycle. Next, we have data location. Where is the data going to be stored? We have object storage, which performs best for big content and high stream throughput. Think of storing PDF files, graphics files, audio, video files, things like that. As far as geography goes, objects are typically stored across multiple regions, often through a cloud provider like IBM Cloud or Microsoft Azure. Object storage is typically highly scalable, seemingly infinitely to petabyte and beyond. Object storage at cloud providers like Google Cloud Storage offers at least 4 nines of high availability and often 11 to 15 nines of durability. Object storage has additional metadata with it. It's extensible metadata. So this customizable data about data allows it to be easily organized and retrieved. It's better for versioning, and it's extensible. It feeds into analytics. Block storage is traditional, gives us strong performance with database and transactional data, often stored on hard disk drives, solid-state drives, in RAID arrays being accessed by storage area networking, to name one topology. However, with block storage, the greater the distance between the storage and the application, the higher the latency. That's a consideration. Because block storage is part of a file system and it's being accessed and addressed that way, we don't really have the extensibility. We typically are part of some type of tree structure that does limit scalability, whereas objects are more flat, more of a horizontal structure. In other words, objects are typically accessed through APIs and HTTPS URLs, whereas data stored in blocks are using a file system, and it's not really extensible, so there's no metadata. This is a great table to kind of refer to for the exam. We have different types of databases. There are relational databases, which are traditional for e-commerce and transactional types of things. There's the key value or NoSQL database, which we use for high volume web apps, gaming applications, in-memory storage. So for example, using memcached or Redis clusters of in-memory only storage for caching, other things like that. We have document databases that are, again, document and key value are highly related. Okay, there's wide column, there's relatively new graph type databases that are excellent for creating relationships between the nodes. So we have these for fraud detection, to create profiles of social networking and social media usage, recommendation engines, social scores, things that countries would be doing to their citizens. There's time-sensitive and time series databases, and of course, ledger databases that are built on blockchain technology, immutable, transparent, verifiable systems of record, supply chain, banking transactions, and of course, cyber currencies. So once we have the collection of the data, the capture of the data, then we determine the location of the data, either object storage or various options of database storage in blocks. We have data maintenance. Maintenance is initiated once the data has been collected and located. Maintenance involves offering data to points where usage and synthesis happen. In other words, some models have this as the transition from raw data to information, usable information, meaningful information. Data maintenance is also about processing the data without yet deriving any value from it for the enterprise. That's where information becomes knowledge, and then in the final phase, ultimately wisdom. Maintenance involves processes such as movement, integration, cleansing, augmentation, deduplication, and the familiar ETL, extract, transform, load functions. Maintenance is the goal of a far-reaching array of data management activities, and because of this, data governance faces many challenges in the area of data maintenance. Next, we have data remnants. Data remnants is the data, metadata, and artifacts that are left over after a software deletion process or a software move action or move process. This is known residual risk when handling data during the life cycle. To counter the risk of malicious data recovery, physical destruction is always the best choice. However, there's other methods. There's fundamentally three categories of ways to handle data remnants. One, we can clear it. Clearing or cleaning involves wiping or overwriting the data with zeros or ones. The data may be recoverable under the clearing method. Then there's purging. Purging is stronger than clearing. It's a more enduring form that can include methods like sanitizing or degaussing, which is basically a magnetic process. Data is not considered recoverable by any known methods after purging. The strongest technique is destruction. This includes shredding, pulverizing, burning the disk or the media, and you could also put encryption into this. In some organizations, how long a particular document or record is stored can be just as important as what is being stored. A data retention policy helps to define what is stored, how it's stored, and how long it is stored, and how it's disposed of when the time arrives. Realize with data retention, it can go back to data location, whereas fresher, more pertinent data can be stored transactionally, and then archived or long-term storage data can go to object storage. So data retention often involves different types of location at different points in time during a workflow or a life cycle. Periodic audits help to ensure that data records or documents are removed when they are no longer needed. And you should implement an automated disk or object storage lifecycle, either on-prem or you can do this using tools in the cloud. In some scenarios, for example in Amazon Web Services, you can deploy a storage gateway, either a rack mount device or installed into a hypervisor, and that storage gateway can connect with a high-speed connection to your service provider partner of Amazon Web Services, and you can use that for a wide variety of different data lifecycle management processes, including database migration, backup and restore, disaster recovery, a wide variety of different services. In this final lesson, let's dig deeper into that last or that final phase or stage of the data lifecycle. That's asset disposal or disposition. In the asset disposal process or phase, plans are developed for discarding system information, physical hardware, software, and making transitions often to a new system. The information, hardware, and/or software may be moved to another system, or may be archived, it may be discarded, or it may be destroyed or disposed of. If performed improperly, the disposal phase can result in the unauthorized disclosure of sensitive data. In fact, it is at this phase where the most vulnerability is introduced when it comes to data storage or data at rest. When archiving information, organizations should consider the need and methods for future retrieval, if any. The disposal activities ensure the orderly termination of the system, or data, or software, and preserve vital information about the system so that some or all of it can be reactivated in the future if necessary. Emphasis is given to proper preservation of the data processed by the system so that data is effectively migrated to another system or archived in accordance with applicable records management regulations and policies for potential future access. So really the bottom line here from a CISSP standpoint is asset disposal and disposition must consider the need for potential future access or retrieval of that data before that decision is made to destroy. The removal of information from a storage medium, such as a hard disk or tape, should be done in accordance with the organization's security requirements. There are several ways to destroy or sanitize. There's burning, shredding, pulping, and pulverizing for paper records. We use pulverizing for microfilm or microfiche. We can also pulverize laser discs or optical discs and document imaging applications. For computerized data, we can do magnetic degaussing. We can do shredding or cutting for DVDs as well. Degaussing can also involve demagnetizing magnetic tapes. In other words, removing the magnetic field. Purging means clearing everything off the media. Wiping involves overwriting every sector of a drive with zeros and ones. For example, the DoD 5220.22-M sanitation method is one of the most common sanitation methods used in data destruction software, and in general is still perceived as an industry standard in the United States. And then there's encryption, encrypting all files before deleting or disposing of the media. Here's an example. Medical offices should maintain documentation of the destruction of health records, including the following: the date of destruction, the method of destruction, description of the disposed records, of course, stripping out any PII or PHI, inclusive dates, and a statement that the records were destroyed in the normal course of business, as well as the signatures of the individuals supervising and witnessing the destruction. Digital signatures in the situation would be acceptable. In this course on asset classification and lifecycle, we explored data and asset states and classification, information and asset handling requirements, data roles and the data lifecycle, and asset destruction and sanitation. In the next course, we'll look at risk assessment, risk analysis and management, countermeasure selection and implementation, and monitoring, measuring, and reporting risk. Well, since this entire course is on risk management, it makes sense to start out defining risk. First, we have what's called inherent risk. Inherent risk is an assessed level of raw or untreated risk. It can be defined as the natural level of risk inherent in a process or an activity, system, application, without doing anything to reduce the likelihood of attack or mitigate the severity of a mishap. Another definition is the current risk level given the existing set of controls, which may be incomplete or less than ideal, rather than an absence of any controls. Residual risk is the amount of risk or danger associated with an action or event remaining after natural or inherent risks have been reduced using risk controls. The general formula to calculate residual risk is residual risk equals inherent risk minus the impact of risk controls. Some methodologies, such as open fair, define impact of risk controls as increasing the resistance or difficulty against threat actors and threat agents. As a review, let's look at the 4 types of risk treatment or handling, also referred to as risk appetite. These will affect the type of controls and the resources used to implement those controls based on different asset classes of vulnerability. First, we have risk avoidance. This is stopping or rejecting the activity that introduces the risk. For example, deciding not to process credit cards on your web servers that you host in your headquarters DMZ. Risk transference or sharing. The risk is transferred, for example, to an insurance company with a cybersecurity rider or to a cloud provider with their shared responsibility model. Risk reduction or risk mitigation. Here, the risk is reduced to an acceptable level by implementing controls. The important principle here is not to expend more resources in people, time, and money than the value of the asset you're trying to protect. That includes the long-term revenue-gaining characteristics of that asset. For example, a relational database management system. And then risk acceptance, tolerating the potential loss by introducing no countermeasures or controls. In other words, not purchasing flood insurance because your facility is not in a flood zone. Just like we have to define risk and define the way we're going to treat risk, we have to define vulnerability. Vulnerability should be quantified as much as possible. For example, as a percentage of probability. Most executive managers and C-suites and C-teams and steering committees would like to see some real numbers, not just a list of potential disasters. You want to deliver meaningful metrics that display the likelihood that a threat agent's actions will result in a loss, including the loss frequency and loss magnitude or impact. Vulnerability can be a derived value based on the threat capability of actors and agents, combined with the resistance of your existing security controls. Going hand in hand with assessing vulnerability is making sure that you've assessed your assets, you've labeled them, and you've categorized them and prioritized them. Why? You'd like to begin assessing vulnerability with the most valuable mission-critical assets. For example, your client and server operating systems. Understanding the posture of patches, your updates, and security fixes. Creating a baseline for the browsers that you're using, the client software, the versions, and the types of endpoints, workstations, laptops, mobile devices, pads, and IoT components, as well as embedded software. You must understand the methods of access for data in transit, wired, wireless, VPN, cellular. Understand the posture of your remote networkers. Have a broad understanding of the available control types and categories that are used at your organization. And are you using two-factor or multi-factor authentication? This is just a starting point. When we're assessing vulnerability, something we're looking for on an ongoing basis is an indicator of compromise, an IOC. These are network or host-based cyber observables. These are forensic artifacts of an incursion or a disturbance. In other words, they're part of an attack kill chain. It's a measurable event or a stateful property in your controlled cyber domain. They could be things like registry entries, compressed files, encrypted files on disk, IP addresses, code running in memory, and other unrecognized files. There are a wide variety of tools that we can use to gather information for vulnerability assessment. Obviously, we have various logs that are output from systems, applications, firewalls, and sensors, and more. We have SNMP version 2C and version 3 traps or informs, information systems and NetFlow collectors. We have security information and event management or SIEM systems, next generation IPS alerts and logs, cloud-based visibility tools, tools that we run in the cloud, at the cloud service provider's IaaS or PaaS, infrastructure as a service or platform as a service, or using those cloud-based tools on premises or on-prem. And lately, using machine learning engines and artificial intelligence AI data analysis. Another valuable tool is online vulnerability databases. This is a collection and distribution of information about exposed computer security vulnerabilities. It typically categorizes and defines an identified vulnerability and its variants along with a timeline and coding. The database usually assesses the potential impact on affected systems based on a qualitative scale, for example, a scale of 1 to 5 or a scale of 1 to 10, often mapping that to colors like green, yellow, and red. Vulnerability databases may also provide mitigations, countermeasures, workarounds, and hyperlinks to various updates and security fixes. Two of the most trusted and often used resources are the Common Vulnerabilities and Exposures CVE, which is a list of entities from MITRE.org that represents publicly known cybersecurity vulnerabilities. It consists of an ID number, a description, and public references. The CVE is used by the National Vulnerability Database, the NVD. Along with that, we have the Common Vulnerability Scoring System, CVSS. This is an open standard for weighing the severity of computer system vulnerabilities. It uses a uniform and consistent scoring method ranging from 0 to 10, with 10 being the highest severity. Besides the CVE with MITRE, we have the National Vulnerability Database with NIST, ISS X-Force Database, Symantec Security Focus BID Database, and At Risk from SANS.org. When you have time, do a web safari to these 5 websites and explore these vulnerability databases to broaden your knowledge for the exam. Working in concert with vulnerability databases is vulnerability scanning. Obviously, HTTP and HTTPS is the most common traffic. So, for example, web application vulnerability scanners are the most common due to heavy usage of HTTP and HTTPS. For example, Burp Suite and OWASP Zap. These are automated tools that can scan web applications and look for common security vulnerabilities, such as cross-site scripting, cross-site request forgery, SQL and command injection, path traversal, and insecure server configuration. Another emerging threat that must be assessed is access to the dark web. The dark web is also called an overlay network or a darknet. You need special software, configurations, or authorization through special tools to access the dark web, which, by the way, your employees may be doing, or vendors' employees as part of the supply chain. The deep web or the dark web is not indexed by search engines. It's an elaborate peer-to-peer network that can be accessed by Tor browsers, Freenet, I2P, and Riffle, to name a few. And on the dark web, your employees and your partners' employees and vendors' employees can find pretty much anything and everything they want. You can also assess vulnerabilities by using open source intelligence tools, or OSINT. This is any data or information that can be collected legally from free public sources concerning an individual, for example, an employee, or an entire organization, for example, a potential strategic partner. It's usually information found on the internet, but it can be sourced from books or reports in a public library, articles in a newspaper or magazine, or statements in a press release, and Freedom of Information Act reporting. And it's not necessary to do this manually. You can gather this information using tools like Maltego, sharing centers, and code repositories like GitHub, among others. Other threat intelligence sources would be Automated Indicator Sharing, AIS. This comes from the Cybersecurity and Infrastructure Security Agency, CISA. This capability enables the real-time exchange of machine-readable cyber threat indicators. There's also STIX, the Structured Threat Information Exchange. This is a standardized language developed by MITRE in a collaborative way to represent structured information about cyber threats. TAXII is the Trusted Automated Exchange of Indicator Information. This is a transport vehicle for services and message exchanges to allow the sharing of information about cyber threats. Other threat intelligence sources would be predictive analysis tools and threat maps, using cutting-edge machine learning and artificial intelligence tools to better predict future threats. In this lesson, we're going to explore risk assessment and analysis. This all begins with documentation. We want to have a risk assessment document to record the processes used to identify the probable threats and propose subsequent action plans if the hazard occurs. We want to document assets at risk, such as people, buildings, information technology, utility systems, machinery, raw materials, and finished goods, not to mention data, applications, and systems. And there are many templates and prototypes available online. The inputs to our document would be identifying the hazards, for example, fire, natural hazards, terrorism, pandemic disease, mechanical breakdown, or cyber attacks. We want to characterize the properties of those hazards and the potential magnitude, which leads to identifying and assessing the assets at risk from these hazards: people, the supply chain, information technology, our reputation or confidence of our organization, and the environment, as well as regulatory and contractual obligations. The output from this should be measurable vulnerability, preferably in a quantitative format, analyzing the impact and magnitude, casualties, business interruption, financial loss, fines and penalties, and lawsuits. This information comes from ready.gov. Part of our documentation may be a risk and threat matrix. In this matrix, on the horizontal axis, we see different event types: accidental data leaks, espionage, financial fraud, misuse, opportunistic data theft, physical theft, product or service alteration, sabotage, and violence. On the vertical axis, we see non-hostile, hostile, and unknown actors or agents. As you examine this diagram, notice that the one hostile actor who has the potential to unleash every event type is the disgruntled insider. That should be considered your highest vulnerability when it comes to internal structured threat actors. Remember, the disgruntled insider could be a present employee or someone who just left the company. Risk assessment leads to risk analysis. Here's a classic qualitative analysis where we use scales of 1 to 5 or 1 to 10. So, for example, for a certain asset or an asset class and a particular scenario or threat, we have the likelihood, 1 being improbable, 5 being frequent. For impact or magnitude, we have 1 being negligible and 5 being disastrous. From this information, we compare this to our asset and the particular threat, and we come up with a heat map. So our vulnerable assets that have a likelihood or probability of likely or frequent, with moderate or critical or disastrous impact will go into the high area. And that's where we should begin introducing our technical, administrative, physical, and operational controls. The challenge to qualitative analysis, however, is that it's relative and more subject to bias. In addition, it's more difficult to determine exactly what is occasional versus likely, or minor versus moderate. Notice there's no 2.5 or 3.7. In other words, there's no nuance involved. What many organizations will do is perform a semi-quantitative analysis based on their qualitative analysis, which may be mature, well-established, and heavily invested. In this case, they'll attach some real numbers to the labels. So, for example, negligible, a value of 1 means no impact. Moderate, a value of 3, for this organization means greater than or equal to $1 million, where disastrous is complete impact, or catastrophic. The likelihood, improbable, equals 1, which is rare or almost never. Occasional, a value of 3, once in the last 5 years, but not in the last year. And frequent equals 5, which is several times a year. So the risk of a particular event on a particular asset may be 4 times 3 equals 12. And you can compare those numbers based on assets and scenarios to better determine where to expend your resources for countermeasures, raising difficulty and resistance. There's also classic quantitative analysis. Here we see the classic Dr. Michael Whitman equation. We have ALE, annualized loss expectancy. This is the expected monetary loss that you would expect for an asset due to a risk over a 1-year period. The asset could be a mobile device, valuables in a safe, a security appliance, data at rest, credit card transactions, etc. Or you could apply this to an entire asset class or an entire rack in the data center. An important aspect of the ALE is it can be used directly in your cost-benefit analysis. If a threat or risk has an ALE of 5,000, then it's probably not worth spending $10,000 a year to mitigate the threat. ALE equals AV times EF. AV is the value of the asset, a monetary value, times EF, the exposure factor. EF is expressed as a percentage of financial value loss from a single incident. It's the percentage of the asset's total value. So AV times EF is our SLE, our single loss expectancy. If SLE equals AV times EF, then the annualized loss expectancy equals SLE times the ARO, the annualized rate of occurrence. This is described as an estimated frequency of the threat occurring in the 1-year period. If we expect this incident to occur every 2 years, for example 0.5, then the ALE would be calculated as SLE times ARO, or for example 30,000 times 0.5, which gives us an ALE of 15,000. If it was once every 3 years, we'd have an ALE of 10,000. These values should help us determine how we'll treat or handle risk on an asset or asset class basis under various probable scenarios, and will populate the risk register. As a reminder, ALE is annualized loss expectancy, AV is the asset value, EF is the exposure factor, SLE is single loss expectancy, and ARO is the annualized rate of occurrence. In this formula, we have the 3 components of risk. On a time frame, in this case, a fiscal year or an annual year, we have magnitude or impact, and we have probability or likelihood. Another emerging method is factor analysis of information risk, or FAIR. Here, risk is determined over a particular time frame based on loss event frequency and loss magnitude. The loss event frequency is based on the threat event frequency and level of vulnerability. All of these values should be a percentage. Loss magnitude is defined by primary loss, or primary losses, and secondary loss, or secondary losses. The goal here is to get calibrated estimates using Monte Carlo simulations, PERT charts, and other formulas. If necessary, you can decompose this even further. For example, the loss event frequency. To determine loss event frequency, we begin with the threat event frequency and the vulnerability level. However, we may need to further decompose that to get more accurate calibrated estimates. So for example, to determine threat event frequency, we'll look at the frequency of contact by the threat actor or the threat agent, and the probability of action by the threat agent or threat actor. We can also break down or decompose vulnerability into the threat capability of the actor and our level of difficulty or resistance through our technical, administrative, operational, and physical controls. Now, several times so far throughout this training, we've already alluded to security controls. Let's review different security control categories and types to make sure that we have these down for the CISSP exam. Administrative controls are also referred to as managerial controls. This would be policies, procedures, best practices, and guidelines. Things like password policies, hiring and screening policies, mandatory vacations, and security awareness training. Then we have the category of technical controls. These control access to a resource using hardware and software components. They can be physical, they can be virtual. Talking about firewall systems, using encryption mechanisms, enforcing passwords with identity and access management and multi-factor authentication. For example, using biometrics or smart cards. It could be IDS or IPS sensors, both host-based or network-based. Then we have physical controls. This is access to the campus, to the facilities, or specific areas or rooms, using things like locks, fences, guards, video cameras, gates, bollards, and more. Here's some other examples of administrative, technical, and physical. For example, under physical, we see motion detectors, cable conduits, badges, dogs, and alarms. Under administrative or managerial, we see rotation of duties, separation of duties, supervision of employees, and effective termination practices. On the CISSP exam, they may also have a category known as operational. Operational is a combination of technical and physical controls. We also have security control types. We have preventative, which stop an attacker from performing an attack. For example, locks, fences, bollards, security guards. Detective, identifying that an attack is happening. For example, cameras, infrared sensors, or acoustic sensors. Corrective. Corrective restores a system to a particular state before an attack. This is often a difficult concept on the CISSP exam. So an example of a technical corrective control would include patching a system, quarantining a virus, terminating a process either manually or automatically, or rebooting a system. The corrective control would be putting into place an incident response plan. A deterrent discourages the attacker from performing the attack. This could be signage, a software banner, or the presence of one of the other security control types. Seeing a security guard or a camera can in itself be a deterrent. So there can be overlap in these control types. Then there's compensating or recovery. This aids a control, like preventative or detective, that's already in place. This is also a difficult concept. So examples of compensating controls would be things like implementing segregation of duties or separation of duties, SOD, to prevent error and fraud, making sure that at least two individuals are responsible for separate parts of any task or function. Another compensating control is adding supervisory control in certain areas and on certain people. Keep in mind that sometimes an organization is unable to fulfill a particular control requirement, maybe a legitimate technical or business constraint. So if you're unable to meet a requirement, for example, for PCI DSS, you want to make sure that your compensating controls meet some criteria. Do all you can to meet the original intent and rigor of the requirement. Also, try to find some other similar level of defense, something to offset the control that you cannot put in place for some reason. And if you can, go above and beyond in the other control areas as a compensation mechanism. From the standpoint of CISSP, it's important for the security practitioner or the security manager or CISO to have some type of framework for their security guidance and their security governance. There's several popular frameworks from several organizations out there that are very influential. The National Institute of Standards and Technology, NIST, is very influential, especially when it comes to looking at questions you might see on the CISSP exam. This is a big source of their content, and they have a cybersecurity framework that has basically 5 phases to it: identify, protect, detect, respond, and recover. In the identify phase, you'll do your asset management, your asset valuation, your assessments. You'll understand your business model, your value proposition, your service, your product, your environment, and you identify risks by doing risk assessment and analysis and managing those risks, specifically through 4 different risk treatments. In the protect phase, you're going to have awareness of the controls you're going to use. We looked at those previously. That's where you'll have your security awareness and training and education, understanding how to secure your data at rest and data in transit, block-based data storage, object-based data storage, on-prem or in the cloud, protection and procedures for information, ongoing maintenance, and the protective technologies. In the detect area, you're going to look for indicators of compromise, anomalies, and events. Negative events or negative occurrences are incidents. An incident that rises to a critical level is a disaster. You'll perform continuous security monitoring, use a wide variety of detection processes, and have solid communications in play. In respond, you'll do response planning, building your incident response team or your swarm team, also involving good communication, analysis, mitigation techniques, and continual improvements. And in the recovery phase, that's your business continuity or continuity of operations and recovery planning. That also involves backup and restore, business impact analysis, solid communication, and ongoing continual improvements. Another important organization is the CIS, the Center for Internet Security. This is a repository for cybersecurity best practices, tools, threat assessment, and threat awareness. CIS leverages the power of a global IT community to help defend public and private organizations against various cyber threats. Using the CIS benchmarks, that's a consensus-created secure configuration guideline for hardening data, systems, and applications. The CIS controls, the CIS Top 20, is a strict, ordered, and simplified set of cybersecurity best practices and guidelines. It's very popular. It's used by a large number of multinational corporations and cloud service providers. There's also CIS Secure Suite. This is a membership program that offers an automated combination of the CIS benchmarks, CIS controls, and the CIS CAT Pro into a commanding and efficient cybersecurity resource. CIS CAT Pro allows users to evaluate conformance to best practices and guidelines and expand compliance scores on an ongoing basis. Organizations like Amazon Web Services, Google Cloud Platform, and Microsoft Azure, the 3 leaders of the Gartner Quadrant, will partner with the Cloud Security Alliance, the CSA, This is an organization committed to defining and raising awareness of guidance for organizations of all types and sizes to guarantee a secure cloud computing experience. CSA offers the CCM, the Cloud Control Matrix version 4, to ensure handling of requirements that stem from new cloud technologies, new controls, and new security responsibilities, necessary auditability of controls for the organization, and interoperability and compatibility with other standards. As a homework assignment for the CISSP exam, you may want to research some other risk frameworks. For example, COBIT 5 is an overarching, comprehensive business and management framework that supports governance and IT management for enterprises. It's from the ISACA or the ISACA. ISO 31000, Risk Management, are guidelines and principles, a framework and a process for managing risk. It's used by all types of organizations, regardless of the sector or the size or their business activities. This framework can help organizations achieve their security objectives, improve the way they locate opportunities and threats, and help them efficiently allocate and use resources for risk handling. A parallel option would be to use IEC 31010 2019. If you are in the credit card or bank card industry, you'll want to use the Payment Card Industry Data Security Standard PCI DSS. This is a cybersecurity framework that is actually supported by all of the major credit card companies and payment processing companies with the goal to keep credit and debit card numbers safe. And also from ISACA is Risk IT. This framework fills in the gap between generic risk management concepts and a more detailed, comprehensive IT risk management approach. It offers an end-to-end global view of risks related to the use of IT and also a thorough treatment of risk management, all the way from the top flowing down to all the operational modules. Regardless of the framework, it's important for your enterprise to understand that to be able to manage significant types of risk, especially in information systems and IT, you have to leverage existing successful frameworks. In this lesson, I want to return to a diagram that we saw earlier in course number 3. Now, our topic here is countermeasure selection and implementation. Now remember, we want to approach this from more of an IT management standpoint. Throughout the rest of this training course, we will be looking at specific solutions that you would use to provide for security of the perimeter and of the network and of endpoints. But the goal here is to understand as a manager which individuals who have roles and responsibilities from a security standpoint will be implementing perimeter and network security. Is it a different team that will be doing the endpoint security? Maybe it's your enterprise mobility management team that handles that. Most likely application security will be done by developers, software engineers, and data security, maybe your database administrators. If it's a small organization, you might be responsible for implementing the perimeter security, as well as the network security. However, as the organization gets larger, often you'll have more of a modular approach, where different teams or different elements of the Security Operations Center have different zones or different domains. So the same people who implement network security in the sense of network emission control, IPS sensors, protecting the voice over IP, may not be the same people that are putting in place your endpoint security, your antivirus, your anti-malware. As a matter of fact, you may have a patch management group or initiative that is separate from the team that actually deploys the laptops and the mobile devices, that does the imaging of the systems. You may have different people who are there for FDCC compliance and privacy compliance. Your data loss prevention, for example, may not be an on-premises solution. It may be a software as a service or a cloud-based solution. Often application security has a clear demarcation because typically the people in charge of application security are themselves software designers or software engineers or developers and architects. The same team or people that provide perimeter security are probably not the same people who do static app testing and code review, fuzz testing, and dynamic app testing, even though they may be involved with the database secure gateway and the web application firewall. Whether you're using a relational database management system or a document NoSQL style database or other types of solutions, for example, a graph database or quantum ledger database, there's quite a few elements to data security. Obviously, classification of the data, encryption of the data, for example, AES 256 GCM, but the identity and access management, access of the data, that will obviously probably be in line with your network security. So again, as a IT manager, we have to understand who has the authority and who has the responsibility to choose the countermeasures and the controls and to implement those. The selection of those countermeasures may involve a steering committee or a security team or even executive management. And those who do the implementation have to go and get the funding and get the approval before they can deploy this in the Security Operations Center or the Network Operations Center or the corporate LAN or call center or whatever. And of course, there's policy management and all the aspects that go into that. We're talking about risk management right now. We've talked about IT security governance, security awareness training, so several of these issues have been covered so far in this course. We will look at things like penetration testing and application security architecture and design, and continual visibility through monitoring and response, making sure we have the right products and the right services and the right people in place to deliver that continual improvement. In this lesson, we want to explore looking at the success of implementing your security controls. One way that you could do this, one approach, is to use an SCA, a Security Control Assessment. This is a formal evaluation, so it's an official assessment, an overall look at a system or a development project or an application, and you're going to compare this against a predefined set of metrics and controls. The SCA is performed in, with, or independently of a full security test and evaluation, which we call an ST&E. This is performed as part of an official security authorization, for example, for an audit, or as part of a penetration test, or perhaps compliance testing. The SCA and the ST&E will appraise the operational plan, or the planned implementation of your controls. The results are a risk assessment report that represents a gap analysis, documenting the residual system, application, or data risk. Assessment tests conducted should include audits, security reviews, vulnerability scanning, and penetration testing. Now, whether you do a formal SCA and or an ST&E, the end result will be a determination of the maturity level of your security initiative or your organization's security governance. Once you complete your security control assessment, you should be able to determine where you are in the CMM, the Capability Maturity Model. Hopefully, you're not at level 1, which the CMM officially calls Initial. Factor Analysis of Information Risk, FAIR, calls this chaotic, and that's what it is. Your decision-making is a free-for-all. It's based on ad hoc intuition with limited experience, if any, poorly defined decision-making, inconsistent results, not aligned with any type of leadership or mission or charter. There's no defined key risk indicators or key performance indicators or CSFs, critical success factors. In fact, there's very few meaningful metrics, and any success from a security standpoint is based on individual heroics. Level 2 is what we call repeatable. FAIR calls this the implicit mode. The process is not codified. There is no established schema. you're still vulnerable to inconsistency from a security governance standpoint. Poorly aligned standards and practices, any data or reports offered to decision makers is usually superficial. It won't hold up to scrutiny or audit. You have unclear roles and responsibilities. People will make decisions outside their role or responsibility or level of authority. Here, risk is defined purely qualitatively. For example, on a scale of 1 to 5 or a scale of 1 to 10, with very little expert judgment. You may have some established metrics, but they're questionable as to how meaningful they are. Level 3 should be a baseline for almost all organizations. We call this defined, or early explicit as far as FAIR is concerned. We have some standardized terminology, and assessments are up to date. You have better support for your security team. You have improved visibility. You have robust and defensible analysis of your applications, systems, and data. You have established security teams, for example, incident response teams or swarm teams. You have a steering committee. You have a service desk. You've populated your risk register or your risk ledger, and you've defined key performance and key risk indicators, and you have well-calibrated, meaningful metrics. At this point, you might have a more precise, semi-quantitative risk analysis. The best that most organizations can hope for is level 4, mature, explicit, or managed. The processes are controlled, they can be adjusted or adapted to particular projects without measurable loss in quality. You have continual improvement in play. You have visible quality. You have up-to-date risk registers, patch management, vulnerability assessment, penetration testing. The data that you use for risk treatment or your risk handling is accurate. It's based more on quantitative analysis, Whitman or open FAIR, and you've got well-defined and well-tested indicators and metrics, and you're well on your way to being certified or getting the assurance that you need from your governing body or your regulator or whoever is providing your governance. Of course, level 5 is rarely achieved, but it's possible if you have mastery and extreme maturity in one of the frameworks we mentioned earlier, like COBIT 5, ISO IEC, ITIL 4. In this lesson, we're going to look at monitoring and reporting, and let's start out with our SIEM systems, a very popular solution for getting visibility into the enterprise. The term SIEM is a combination of security information management and security event management. SIEM systems, which can be physical or virtual or cloud-based, centralizes the storage and analysis of logs and other security-related documentation to perform near real-time analysis. You can optionally send filtered and processed data to mining, BigQuery activities, and data warehousing servers for machine learning algorithms in your data center or at a cloud service provider. SIEM systems allow security and network professionals to take countermeasures, perform rapid defensive actions, and handle incidents more successfully. An example of a cloud-based SIEM is Microsoft Azure's Sentinel. As you can see in this diagram, SIEM systems have a wide variety of different activities they can perform. Not all systems will perform all of these activities. However, the more broad, the more comprehensive, the better the results from a security standpoint. SIEM systems can collect and analyze logs. They can perform event correlation, deduplication, and normalization. You can use them for forensics, for IT compliance. You can monitor all different types of logs, system, security, application. You can audit object access. You can get real-time alerts, dashboards, reporting. You can perform file integrity monitoring, system and device log monitoring, and of course, log storage and retention. Often, however, the SIEM system will use a different type of storage, either data warehousing or object storage in the cloud to conduct cloud-based BigQuery and machine learning. Some common sources of data that are sent to SIEM systems would be firewall appliances and firewall systems, IDS and IPS sensors, assorted server logs, web servers, email servers, network time protocol servers, directory servers, infrastructure devices, switches, multi-layer switches, and routers, specialty email and web appliances or services, and, of course, system logging, including SNMP, traps, and informs. Obviously, the more that you can automate and orchestrate the security process of visibility and reporting, the better your results. Automation is different than orchestration. IT automation, from a security standpoint, involves generating a single task to run automatically without any human intervention. Automation could involve sending alerts to a SIEM system, dynamically triggering a serverless function at a cloud provider, for example, Azure Functions or AWS Lambda, or adding a record to a database when a batch job is run. Orchestration involves managing several or many automated tasks or processes. It's the more global activity. As opposed to focusing on one task, orchestration combines all of the individual tasks. Orchestration occurs with various technologies, applications, containers, datasets, middleware, systems, and more. For example, historically, we would use Docker to produce a containerized application and something like Kubernetes as an orchestration service for all of our Docker containers. Another solution is SOAR, Security Orchestration, Automation, and Response. SOAR is an assortment of software services and tools. It allows organizations to simplify and aggregate security operations in 3 core areas: threat and vulnerability management, incident response, and security operations automation. Security automation involves performing security-related tasks without the need for human intervention. SOAR can be defensive detection, response, and remediation, or offensive vulnerability assessment and penetration testing used in active defense. You should automate if the process is routine, monotonous, and time-consuming. Now that we've automated our visibility and monitoring using SIEM and SOAR systems, let's generate some meaningful reports. Reports should involve meaningful metrics. Reports should have as much information as necessary or as needed, but should not be a data overload. You may need to express things in simpler terms, or have different reports for different target audiences. The recipients of your reports typically don't have the same technical experience or security knowledge that you do, so it needs to be understood by your target audience. Dashboards are very effective. Often, security engineers will use Python or the R programming language to produce modern, visually engaging reports. So it helps to understand components of visual communication and best practices. You want to avoid 3-dimensional representations. Use a palette of sequential colors and avoid simple pie charts. Opt for scatter plots, bars and bubble charts, Venn diagrams, density plots, and box plots. Utilize tools that deliver meaningful and easily digestible results. Cloud service providers have tools such as CloudWatch, CloudTrail, Operations, and Insights. Create powerful dashboards with maximum visibility using R programming. Generate automated system reports. Provide written PDF summaries. Have engaging charts and graphs. And make sure that you have after-action reports, which include sections on lessons learned, things you did right, things you did wrong, and how you can improve next time. In the next lesson, we'll look specifically at continual improvement life cycles. Let's talk about continual improvement in this lesson, and in doing that, we're going to take this overlay of 3 different models. We'll start with the simple model of plan, do, check, and act, PDCA. So if you're going to have an initiative of continual improvement, obviously you want to do a lot of planning as much as possible, as much information gathering as possible. Then once it's time, you do. You have an action plan. All along the way, you keep checking in an iterative way for ways that you can improve. Once you find ways to improve based on the original do baseline, then you act. And those actions will involve continual improvement and lead to additional planning. So it's a circle that we go through of continual improvement. Let's look next at the 7 steps for continual improvement. First, in the upper right-hand corner, we identify the strategy for improvement. We have a vision. What is the business need or the organizational need? We have strategic goals and we have tactical goals. Strategic goals are more based on governance, your mission, your value proposition. Tactical is the way that we actually implement continual improvement, as well as operational goals. That's an ongoing maintenance. Then, in step 2, define what you will measure. And then in step 3, we gather the data. Notice in that quadrant, we're in the data quadrant, where we just basically are collecting raw data. The who, the what, the when, the criteria, maintaining data integrity, making sure that we are secure by default and secure by design, gathering data for our operational goals and the tools that we're going to use for measurement. Next, we have step 4. How often do we process this data for continual improvement? How do we format it? What type of automation tools and systems do we do? How do we test for accuracy? Notice that in this quadrant, the data now becomes information. Raw data becomes usable information in some type of format, feeding into tools and systems and engines. In 5, we analyze the continual improvement information and we analyze the data. We look for trends. We look for moving targets. We discover what improvements are necessary. This is knowledge. Notice how our information becomes knowledge once we start building in analysis, modeling, trend analysis, and overall discovery of the necessary improvements. In step 6, we present and use the information. This is where we have our assessment summary and our action plans, and then finally, we implement the improvement. Notice that the ultimate implementation of improvement is the wise thing to do. We start with raw data, it becomes information, it gets processed, and then we get analysis, which gives us knowledge, and our ultimate goal, continual improvement, and the wisdom that's derived from this very important process. In this lesson, we will define threat modeling and look at several threat modeling methodologies. The process of threat modeling involves creating an abstraction of a system or a prototype to identify risk and probable threats. This is often done in a private cloud environment or a sandbox, also referred to as a detonation chamber. For example, in the diagram, we're looking at the different stages and phases of malware. So a new malware variant could be tested and launched and analyzed in a sandbox environment or a detonation chamber in your own data center or perhaps at a cloud provider. When this cyber threat modeling is applied to systems that are being developed, it can help us lower vulnerabilities and lower risk. With the widespread adoption of threat intelligence technologies, most enterprises, and this includes government agencies, for example, like the U.S. Department of Defense, cyber threat modeling is extremely important to these federal programs. Department of Homeland Security, DHS, NASA, for example, they're constantly adopting threat-focused approaches to risk management. A structured approach and ongoing processes to analyze the security of systems, application, and data. Threat modeling provides visibility, increased security awareness, and prioritization and understanding of the security posture. But the ultimate goal of threat modeling is to mitigate all threats and prevent future attacks, as well as quickly responding to new variants and zero-day code. STRIDE and PASTA are common threat modeling methods. STRIDE stands for spoofing of user identity, tampering, repudiation, information disclosure, denial of service, and elevation. So in this methodology, there are 6 different categories of malware threats. spoofing, tampering, repudiation, information disclosure, DOS, and elevation or escalation of privileges. It's a threat model initially developed by Microsoft back in 1999, and it has 6 classes that represent attackers' prevalent goals. PASTA stands for Process for Attack Simulation and Threat Analysis. It's a risk-oriented method that endeavors to link business objectives to technical requirements. PASTA has 7 stages with the goal of delivering a dynamic process ranging from identification in stage 1 to enumeration to scoring in stage 7. Trike and VAST are 2 other common modeling solutions, along with DREAD. Trike is a technique frequently used as a risk management tool during security audits. It is a unique open-source threat modeling method focused on enhancing the security auditing process from a cyber risk management perspective. VAST is Visual, Agile, and Simple Threat Modeling. VAST attempts to address the limitations of other threat methodologies, such as DREAD, STRIDE, and PASTA, by using a more practical approach. The founding principle of VAST is that in order to be effective, threat modeling must scale across the infrastructure and the entire DevOps portfolio. VAST has separate operational models and application models. In this final lesson, we're going to explore Supply Chain Risk Management, SCRM. A huge challenge to modern supply chains is that several, even thousands of suppliers can actually contribute to a single product. Many risks exist because vendors' employees, for example, may introduce cybersecurity vulnerabilities from hardware, software, and services used in the chain. Some tiers of the supply chain may be considered proprietary as well, so that a lack of visibility impedes the security lifecycle. This can make third-party assessment and monitoring more difficult. In other words, it can be almost impossible to do security control awareness at certain points in the chain. At the heart of SCRM is delivering meaningful metrics and analysis related to exposing specific areas of the supply chain. For example, cargo disruption trends, exposing transit modalities, the threats that are posed by terrorist groups or activist groups and other criminal syndicates. There are country risk variables, such as the rule of law, and the effectiveness or inability to provide law enforcement at different phases of the chain when dealing internationally. Governments continually work with the trade community to manage and mitigate supply chain security risk. Weaknesses in the supply chain, for example, were exposed, especially during the year 2020 during the global pandemic. From a U.S. point of view, the U.S. Customs and Border Protection, CBP, and Customs Trade Partnership Against Terrorism, CTPAT programs are heavily involved in supply chain security and risk. Initiatives involve third-party assessment and monitoring, as well as setting minimum security requirements and service-level requirements. Here's an example SCRM process, starting with the NPI, the new product introduction. Notice that we have a life cycle here: plan, source, make internally, then make externally, and then deliver. It's a simple model for a new product, but we have to identify and document risks early on in step 1. In step 2, we create a supply chain risk management framework. In step 3, we monitor risk using customized and automated tools. In step 4, we implement our governance and conduct regular audits. In step 5, we manage unknown risks by building strong defense in depth all along the supply chain whenever possible in a security-aware culture as a partnership between all the members of the supply chain. In this course, Risk Management, you learned about vulnerability and risk assessment, countermeasure selection and implementation, risk frameworks, monitoring, measuring, and reporting, and threat modeling and supply chain risk management. In the next lesson, you'll learn about practical cryptography, cryptographic life cycles and key management, and PKI, public key infrastructure. In this course on practical cryptography, we're going to begin with the type of algorithm that's been around since the beginning of recorded history. We have examples of this from Julius Caesar. We have examples from early in the World Wars. Basically, it's symmetric key algorithms, and it's where the same secret key is used for encryption and decryption. The secret key must be shared between the sender and the receiver in a secure fashion. There's a lot of ways to do this. You can do it out of band. You can do it in band. For example, with a courier or a delivery service or some other secured communication channel, or as we'll see later, we can actually use an asymmetric key crypto system to derive a shared secret key between two parties over an untrusted network. The strength of the symmetric key crypto system is related directly to the management of those keys and the size of those keys and how they're shared. Key lengths are typically from 40 bits to 512 bits. In most circumstances, the key length should not be less than 64 bits in length. Longer keys are less susceptible to a successful brute force attack. Symmetric key algorithms provide wire speed encryption. They're commonly used to encrypt bulk data. For example, data sent between two peers on a site-to-site VPN, or the customer-managed keys used at cloud service providers to encrypt data at rest. Symmetric key algorithms commonly deploy confusion and diffusion techniques added to transposition to make them impervious to attack. And they can be accelerated by hardware, for example, hardware security modules from Gemalto. And these algorithms use stream ciphers, where the bits are XOR'd or exclusive OR in a stream, or they can be block ciphers, where an entire block, let's say of 128 bits, is encrypted. If the final block doesn't have 128 bits, historically, it would be padded up to 128 bits. Block ciphers are often used. There are several modes for symmetric key algorithms. An older mode, a traditional mode, is ECB, Electronic Code Book. This is the simplest mode where each block of data is simply encrypted with the same key, and it leverages a very large code book. A replacement for ECB was CBC, Cipher Block Chaining. We also saw this mode in upgrades to 802.11 wireless networking. CBC improves on electronic codebook by making the encryption of each block dependent on ciphertext of the previous block. We also see this today in the technology we refer to as blockchain. CTM or counter mode generates the next keystream block by encrypting successive values of a counter. By adding counters to block chaining, we make the algorithm less deterministic. And then we have GCM, Galois counter mode. This is an authenticated encryption mode that concurrently combines confidentiality, authenticity, and integrity, and it's based on Galois fields. In Galois counter mode, we use a large initialization vector, or pseudo-random nonce, along with several layers of confusion and diffusion. In addition, we have a counter to make it less deterministic. GCM is also an AEAD, authenticated encryption, authenticated decryption, which means we don't need an extra HMAC, or hashed message authentication code, if we deploy it with its own GMAC. GCM is one of the most popular modes used by Advanced Encryption Standard, AES. AES became effective as a U.S. federal government standard on May 26, 2002, after approval from the Secretary of Commerce. AES is included in the ISO IEC 18033-3 standard. It's available in many different encryption packages, and it's the first and only publicly accessible cipher approved by the NSA for top secret information when used in an NSA-approved cryptographic module. The next category are asymmetric key algorithms. With asymmetric keys, different keys are used for encryption and decryption. Specifically, they're a generated key pair They're generated together, and they're mathematically related. The public key will be shared with many, but the private key, hopefully, is kept secret by the owner or the system that derived the key pair. Asymmetric key algorithm keys range from 512 bits to 4096 bits in length. Asymmetric keys are not used to protect bulk data, but rather smaller amounts of information, like the amount of information in your national ID card or passport or driver's license, or the information in a digital certificate, or a 128-bit symmetric session key. These algorithms are slower, so they're not suitable for bulk data encryption. The design of many asymmetric key algorithms is based on the problem of factoring the product of large prime numbers. As a matter of fact, when using asymmetric algorithms, one of the first actions is to generate a large prime number. Key management of asymmetric algorithms is simpler and more secure, primarily because of public key infrastructure, and it's best suited for digital signatures and session key exchange or agreement protection services. RSA is the most popular commercial asymmetric algorithm, but there's also DSA, elliptic curve DSA, PGP, pretty good privacy, GPG, and others, and the Diffie-Hellman protocol. When using an asymmetric key crypto system for privacy or confidentiality, let's say when Alice wants to send a confidential message to Bob, Alice will first get Bob's public key, which is readily available. For example, in a digital certificate, she will encrypt the message with Bob's public key, and then Bob will decrypt it with his secretly held private key. On the other hand, if Alice wants to send Bob a message and give Bob a high degree of confidence that the message came from Alice, origin authentication, she will encrypt it with her private key, and then Bob will acquire her public key and then decrypt it with Alice's public key. The Diffie-Hellman key exchange is the first key agreement asymmetric algorithm used for generating shared secret keys over an untrusted channel. Once the two parties securely develop shared secrets, they can then use the keys to derive subsequent keys. These keys can then be used with symmetric key algorithms to transmit information in a protected way. Diffie-Hellman can also be used to establish public and private keys. However, RSA tends to be used instead. The RSA algorithm is also capable of signing public key certificates, whereas the Diffie-Hellman key exchange is not. Diffie-Hellman is used by TLS, IPsec, Secure Shell, PGP, and many other uses. In the Diffie-Hellman key exchange, modulo math is used. There are different Diffie-Hellman groups. Diffie-Hellman group 14 is a 20,048-bit modulus. This is the minimum acceptable. Diffie-Hellman group 19 uses a 256-bit elliptic curve as opposed to modulo math. This one's acceptable. Diffie-Hellman group 20 is a 384-bit elliptic curve. This is considered next-generation encryption. And Diffie-Hellman groups 21 and 24 both use elliptic curve and are considered next-generation. The original Diffie-Hellman mode, DH, used the same shared secret all the time between parties. The original DH by itself does not provide authentication of the communicating parties. Diffie-Hellman ephemeral, or ephemeral DH, uses different shared secrets each time between the parties. A cryptographic key is called ephemeral if it's generated for each execution of a key establishment process. Elliptic curve Diffie-Hellman uses EC public and private key pairs. The same shared secret is used all the time between the parties. The very popular ECDHE, elliptical curve ephemeral Diffie-Hellman, uses EC public and private key pairs, and a different shared secret is used each time between the parties. This is emerging as the most popular mode of Diffie-Hellman. In this lesson, we're going to look at cryptographic hashing. A cryptographic hash, also referred to as a hash value, a message digest, a fingerprint or checksum, maps data of any arbitrary length to a fixed length string, for example, 256 bits using SHA-2. It produces a digest from 128 to 512 bits in length. It's based on an irreversible one-way mathematical function. As you can see in the diagram, we input data of arbitrary length into the hash function, and we take the fixed length hash result and we append it or attach it to the original data and send that along to the recipient to meet the goal of integrity in the CIA triad. For a cryptographic hash function to be considered reliable or trustworthy, it should be unfeasible, if not impossible, to generate the original data from the hash value. It should be deterministic and quick to compute, and any small change, for example, 1 bit flipping from 0 to 1 or vice versa, should result in the avalanche effect. In other words, the resulting fixed-length hash should be completely different, and it should be collision resistant. In other words, no two different data or message inputs should generate the same hash value. That's one of the reasons why you should never use MD5 in any new security implementation. MD5 was based on the MD4 algorithm. It should no longer be used. It's been deprecated. SHA-1, which produces a 160-bit digest, should also be set aside in favor of SHA-2, 256-bit SHA, or SHA-3. SHA-3 was not meant to replace SHA-2, but it's highly recommended. You can also use Race Integrity Primitives Evaluation Message Digest, or RIPE-MD, with its 128, 160, 256, and preferably 320-bit versions. Now, hashing alone gives us integrity. However, if we combine a shared secret key with the algorithm, we get origin authentication as well. We call these HMACs, Hashed Message Authentication Codes. The hash is the hash function, for example, SHA-256. The key is the MAC. As you can see here, we want integrity in origin authentication for information sent between routers. This can be inside the organization, or it could be over the internet, using a protocol, let's say, Border Gateway Protocol. The routing update itself is the data. It goes through the hash function combined with a shared secret key, and that gets appended to the routing update. Notice, however, we don't get confidentiality or privacy. To do that, we would use other cryptographic algorithms. Once the other router receives the advertisement or hello or update, it uses the same cryptographic hash algorithm and the shared secret key to make sure that the information has not been changed in transit and that it came from an authenticated source, another party with the same secret key. Here's an example of the same thing, but with a transaction. The transaction is the data that's combined with the shared secret key. And by the way, this shared secret key could be derived using Diffie-Hellman in one of its modes. It could even be a key derived from the original Diffie-Hellman key that goes through the hashing algorithm and then gets appended to the original transaction and sent to the recipient. HMACs are often combined with symmetric key crypto systems to protect data in bulk, getting confidentiality, integrity, and origin authentication. Digital signatures are a form of electronic signature that was designed to replace and/or augment physical handwritten signatures. They're a mathematical algorithm commonly used to validate the authenticity and integrity of a message, such as an email, a credit card or online transaction, or some form of digital document. Realize, digital signatures do not provide confidentiality or privacy. They generate a virtual fingerprint that is unique to an entity and used to identify users and protect information in digital messages or documents, such as a digital certificate. Digital signatures are more secure than other forms of electronic signatures. Let's say a user wants to send a digitally signed purchase order for $100,000 to a vendor. The original purchase order or original data of arbitrary length goes through a SHA-1 or SHA-2 hash. The result is a fingerprint or a digest. The fingerprint or digest is then encrypted or signed using the private key of the sender, in this example, the RSA algorithm. That result is then attached or appended to the original purchase order, sent over the untrusted network, and then the vendor or the recipient will use the public key of the sender, which it got through a authenticated channel or a handshake or possibly in a digital certificate, and using this same hash function unpacks the result, matches the original hash, and concludes that the purchase order has maintained its integrity and there's a high degree of confidence that it came from the authenticated sender because the sender's private key was used. A digital certificate is a form of a file used to tie cryptographic key pairs to entities. such as individuals, websites, devices, or entire organizations. If public trust is needed, then a Trusted Certificate Authority, CA, will assume the role of a third party to validate, identify, and associate them with cryptographic pairs using the digital certificates. In fact, the certificate authority could also generate the key pairs on behalf of the sender or the receiver. The key pair consists of a public key and a private key. The public key is included in the certificate, while the private key is kept secure, or at least that's the goal. The owner of the private key can then use it to sign documents, and the public key can be used to verify the validity of those signatures. A common format for digital certificates is based on the X509 v3 standard, which consists of a public key, a digital signature, and other metadata, such as a unique serial number, about the entity linked to the certificate. Also included is information about the issuing certificate authority. We'll revisit digital certificates when we talk about public key infrastructure, PKI, later on in this course. In this lesson, let's explore advanced forms of cryptography, starting with the aforementioned elliptic curve cryptography. Elliptic curve cryptography uses rich mathematical functions based on points on an elliptic curve. The algorithm computes discrete logarithms of elliptic curves, which is different from calculating discrete logarithms in a finite field. The smaller and more efficient keys offer exceptional speed and strength. For example, a 256 elliptic curve key equals a 3072 normal key. For example, a key used with traditional Diffie-Hellman. Elliptic curve cryptography is used in digital signatures, key distribution, and encryption. It's excellent for mobile devices and IoT. It uses less processing power, and it gets better security with a smaller key space. It's also faster. There are two common public applications of elliptic curve cryptography. There's the elliptic curve digital signature algorithm, ECDSA. This introduces a variant of the digital signature algorithm, DSA, by utilizing the elliptic curve cryptography. However, there exist some political and technical concerns in the usage of ECDSA. More popular is elliptic curve Diffie-Hellman and elliptic curve Diffie-Hellman ephemeral, ECDH and ECDHE. This is a key agreement protocol that's extremely popular. It allows two parties, each having an elliptic curve public-private key pair, to generate a shared secret key, or keying material, over an insecure channel. This shared secret may be directly used as a key, or it may derive another key. The key, or the derived key, can then be used to encrypt successive communications using a symmetric key cipher. Quantum computing. Personal computers use bits, ones and zeros, whereas quantum computers use qubits. Qubits are typically subatomic particles, such as electrons or photons. Quantum computing derives its power from the fact that qubits can represent numerous possible combinations of 1 and 0 at the same time. This ability to simultaneously be in multiple states is called superposition. Post-quantum cryptography involves developing new crypto systems that can be implemented using today's existing computers, but that will be resistant to attacks from tomorrow's quantum computers, which are much more powerful, much faster, and stronger. Post-quantum computing involves increasing the size of digital keys, developing more complex trapdoor functions, lattice-based cryptography, and super-singular isogeny key exchange. Quantum communications is the combination of quantum physics and computing. Quantum communication leverages the laws of quantum physics and quantum computing to protect data. Some organizations are transmitting highly sensitive data using QKD, quantum key distribution. QKD sends encrypted data as normal bits over the network, while the decryption key information is encoded and transmitted in a quantum state using the aforementioned qubits. These networks are theoretically ultra-secure. Homomorphic encryption helps us protect data in use, or data resident in volatile memory. Data remains encrypted while still being processed. Cloud service providers like AWS, for example, can apply homomorphic encryption functions on the encrypted data. For example, in a Redis Elasticache. This encryption commonly uses public-private key pairs, and it gets its results by using algebraic operations on the encrypted ciphertext. One of the general truths about cryptography is that the main weakness of crypto systems is in the key life cycle. Obviously, that introduces the human factor. So in this lesson, we're going to look at a key management life cycle. Keys can be generated through the key manager, which could be software, hardware security modules, managed by a key owner or custodian, and it can be done through a trusted third party. Regardless, you're using a cryptographically secure random or pseudo-random bit generator. The keys, along with their attributes, will then be stored in the key storage database, which again could be an HSM and must be encrypted by a master key. Other attributes or metadata include name, activation date, size, and instance, and those keys may be cryptographically hashed. A key can then be activated upon its creation or set to be activated automatically or manually at a later date and time. After key generation, we have key distribution and loading. The objective of distribution and loading is to install the new key into a secure cryptographic device, either manually or electronically. This could be into, let's say, a secure enclave on a mobile device. For manual distribution, keys must be distributed and loaded in key shares to avoid the full key being viewed in the clear. When symmetric keys are installed, it is recommended that they be encrypted by a public key or key encryption key prior to being delivered for deployment. The key should be deployed and tested for a certain time period to ensure that operations are successful in order to avoid any potential data loss or theft. After key distribution and loading, we have key backup and key storage. In order to recover a key that's been lost during its use, a secure backup copy should be made available. Backup keys can be stored in a protected form on external media, CD optical disk, USB drive, a cybercurrency hard wallet, one that uses a USB cable or a camera. It could be a hardware security module, HSM, or by using an existing traditional backup solution, either local or over the network. When a symmetric key or an asymmetric private key is being backed up, it must also be encrypted and stored. It's also helpful to use mirroring or RAID arrays for high availability and redundancy. Another part of the key lifecycle is the normal use and replacement of keys. The key management system should allow an activated key to be retrieved by authorized systems and authorized users. The system should also effortlessly manage current and past instances of the encryption key. The key manager will replace a key automatically through a previously established schedule, or if it's suspected of compromise. For example, an access key at a cloud service provider that's being used by programmatic users or service accounts. When replacing keys, the goal is to bring an extra key into active use by the system and to convert all stored, secure data with the new key. Archival refers to offline long-term storage for keys that are no longer in operation. Long-term storage can be accomplished with Gemalto hardware security modules or cloud-based HSM. These keys usually have data associated with them that may be needed for future reference, such as long-term storage of emails. There may also be associated data or metadata in other external systems. We call this remnants. When archiving a key, it must be encrypted to add security. And before a key is archived, it should be proven that no data is still being secured with the old key. The final phase of the life cycle is key disposal or key disposition. All instances or certain instances should be completely removed. The end of life for a key should only occur after an adequately long archival phase and after adequate analysis to ensure that loss of the key will not correspond to loss of any data or loss of any other useful keys. There are 3 ways to remove a key from operation: key destruction, key deletion, and key termination. The most effective is key destruction. Key stretching is the process of lengthening symmetric keys to at least 128 bits. The initial key, the password or passphrase, is fed into an algorithm, and an enhanced key is produced after many iterations. This increases the time it takes to perform brute force attacks on a key. Common algorithms are bcrypt and PBKDF2. Key stretching can be done by password managers, software tools, HSMs, or using other protocols like WPA3 for wireless. Key escrow is where a third party has a copy or has access to private keys. They're only allowed access under strict conditions, for example, a court order. This could be cloud service providers, it could be cybercurrency exchanges, or other third-party entities that deal with symmetric keys, private and public keys, for example, certificate authorities. Issues can arise with key escrow. For example, the request for access process can be expensive or complicated. Some entity has to authorize the legitimacy of a request, and there's the risk of granting the access. And what's the vulnerability of the systems involved in the key escrow process? I've mentioned the term HSM, or Hardware Security Module, several times. This is a tamper-proof hardened device that provides crypto processing and protection of cryptographic keys and functions. Now realize the HSM can be a physical 1-rack unit or 2-rack unit device, but HSMs can also be installed in hypervisor situations. This allows for multi-tenancy or abstracted HSM or HSAs. HSMs involve partitioned administration and strict security domains. They can be used to apply corporate key use policies, for example, to be compliant to GDPR, PCI DSS, Sarbanes-Oxley, and others. HSMs can be used in place of software crypto libraries and SSL/TLS accelerators. Key administrators can access HSMs either over a network or more often in an out-of-band method with direct connectivity from a management device. And they can store symmetric keys and asymmetric keys and be involved in every phase of the key management lifecycle. On the CISSP exam, it's important to be familiar with public key infrastructure, or PKI, especially from a management standpoint. PKI is based on the concept of the trusted introducer that came from PGP. In other words, the trusted third party in a web of trust is the certificate authority. In its most basic form, PKI is a scalable method for securely distributing and revoking public keys on a global basis. There are many CAs, or certificate authorities. These are trusted introducers. Companies like Komodo, GeoTrust, DigiCert, and Thought. These organizations securely store, issue, and sign certificates. And in some situations, they may actually generate public and private key pairs on behalf of clients. In the diagram, user A generates a public and private key pair, for example, using RSA. So they have a private and public key. They will also get the public key of the certificate authority. That'll be stored in some root storage on an operating system or in a browser store. The user's public key is stored in a digital certificate issued by the CA, and the CA will sign or encrypt that certificate with their private key. Certificates can now be exchanged over untrusted networks, as their certificates and public keys of entities are now verified with the public key of a certificate authority. User A and user C can now conduct transactions. It's important, however, that early on, the exchange of digital certificates between user A and user C be done over a trusted channel or a secure channel, for example, transport layer security or IPsec. In addition, user A and user C don't necessarily have to have the root certificate of the same certificate authority, because there's a web of trust between CAs globally on the internet. Two public key algorithms will be involved. There's one within the certificate. This is the subject's public key algorithm, for example, some 160-bit elliptic curve mechanism, and the one that was used by the certificate authority to sign or encrypt the certificate, such as RSA 2048. Those two algorithms will be in the digital certificate, along with a serial number, a subject alternative name, for example, an IP address or a fully qualified domain name, and other extensions to offer better security. CAs will have a hierarchical trust model. Realize that the certificate authority can be an enterprise CA within an organization, or it could be a public CA like Komodo or GoDaddy, or you can install a CA on an edge device for a VPN gateway. There's several applications. Regardless, there is a hierarchy. The root CA provides certificates to intermediate CAs, if you have them. Intermediate CAs provide certificates to users and other down-level intermediate CAs. The root could be online, or, for security reasons, it could be offline or air-gapped. If it's online, it's connected to the network, and it issues certificates over the network. If it's offline, it's disconnected, and it issues certificates on removable media. Certificate chaining is very important. It's referred to as a trust delegation, where each CA signs the public key of the CA one level below. Alternatively, it's very common for CAs to cross-certify each other without some strict hierarchical relationship being in place. That goes back to earlier when I said user A and user C don't necessarily have to have the root certificate of the same CA on their systems or their browser store. The CA must be in trusted store, but it's not possible to include all CAs. A chain of trust is established by an issued to field and a issued by field. In the diagram, the root CA issues a certificate to intermediate 1. Then intermediate 1 issues one to intermediate 2. This will be in the certificate issued to the user, which can be a person, an organization, a system, or a device. If the primary goal of PKI is to securely globally distribute public keys and certificates, the secondary goal is to revoke a certificate when it's no longer valid. The CRL, Certificate Revocation List, is the original method using a list of certificates that are invalid based on the serial number. The CRL is issued by the certificate authority who granted the certificate, and the CA also determines how often this is updated, generated, and published. It can be done in defined intervals, for example, every 4 hours, or pushed immediately. It can also be downloaded by clients regularly, but not in real time. Realize that suspending a certificate is not the same as revoking a certificate. Suspension does not place the serial number on the certificate revocation list. So, if someone loses a device or goes on a leave of absence, you can suspend the certificate as opposed to revoking it. A newer method built on the CRL concept is Online Certificate Status Protocol, or OCSP. This is a method for a web browser, for example, to determine the validity of an SSL TLS certificate by verifying with the vendor of the certificate. It's an online transactional database built on the concept of the CRL by using the serial numbers generated and published immediately. Clients can query the database anytime, although many, such as web browsers, will bypass this process. OCSP improves security, but it can cause websites to load slower. Also, not all vendors and websites support OCSP because of the impact on interoperability or for financial competitive reasons. OCSP stapling is a method for quickly and safely determining whether a TLS server certificate is valid. Stapling involves the web server downloading a copy of the vendor's response, which it can then deliver directly to the browser or some other web client. The web server can provide the browser information on the validity of its own certificates instead of requesting the information from the certificate's vendor. To provide OCSP stapling, a status_request_extension in TLS 1.2 or higher is used by the web client to indicate support for this feature. The TLS server will send fresh certificate information in the TLS handshake protocol. Stapling supports only one OCSP response and is used to check the status of the server certificate only. And finally, we have certificate pinning. This is a security method for associating a service with certificates and public keys. It offers 3 key improvements. It reduces the attack surface by letting owners pin the CAs that are allowed to issue certificates for their domain names. Realize any CA can issue a certificate for any domain. For example, Google preloaded public key pinning for most of their sites starting in Chrome 13 browsers. Pinning provides key continuity without relying upon public certificate authorities. Pinning can be used for authentication using a secure channel. For example, transport layer security. Cryptology is made up of two disciplines: cryptography, which is the creation and generation of cryptosystems, and cryptanalysis. Cryptanalysis is the study and practice of exploiting weaknesses in communication protocols and cryptosystems. Most known methods of cryptanalysis, like brute force, are ineffective in most situations and on most modern cryptographic algorithms, based on the fact of there's not enough time, there's a lack of computing power with the exception of quantum computing, and there's good key management and good life cycles because of automation and orchestration, or cloud-based key management services and HSMs. Most weaknesses are found in the implementation and key management as opposed to the algorithm itself. Classical cryptanalysis typically involves two disciplines: mathematical analysis, that involves analytical attacks which exploit the internal structure of the encryption methods, and brute force analysis, which treats the algorithm as a black box and tries all possible keys in the key space. We also have implementation attacks. The most common implementation attack is a side channel attack, where one would measure the electrical power consumption of a processor operating on a secret key. The power trace is used to determine zeros and ones and ultimately gives information about plaintext or keys. To be successful with an implementation attack, you typically need physical access, let's say to a smart card or an HSM, or be in proximity to a wireless access point. Another form of cryptanalysis is to perform social engineering. This involves the exploitation of human weaknesses by leveraging the ability to trick, coerce, or extort a subject for information. It can involve spoofing, hoaxing, shoulder surfing, dumpster diving, phishing attacks, and more. Most attackers will attempt to find vulnerabilities through social engineering before using other cryptanalytic methods, which are more time-consuming and costly from a resource standpoint. For example, let's look at attacking the RSA protocol, the most common commercial asymmetric key crypto system. You can do a protocol attack to exploit weaknesses in the way that RSA is used. However, padding and proper implementation can countermeasure protocol attacks. Then you have mathematical attacks. The best example would be to use quantum computing to factor the modulus. Although 1024-bit RSA is adequate, a modulus of 2048 to 4096 bits is highly recommended in all new security implementations today. Or consider using elliptic curve. Then there's side channel attacks. Information about the private key is leaked via a physical channel, such as power consumption, SPA, and timing behavior. In this course on practical cryptography, you learned about cryptographic methods, digital signatures and digital certificates, key life cycles, management, and public key infrastructure, PKI, and advanced cryptography and cryptanalytic attacks. Coming up in the next course, you'll learn about controlling physical and logical access, access control architectures, and access models. Now, as we dive into this course, I want to emphasize the fact that in Course 12, coming up later, we're going to dedicate that to site and facility security. What we're going to mention here in our first lesson is the importance in identity and access management to remember it's not just logical access that we need identity access control, but physical access as well. So we're going to touch on that real quickly here. And remember that we're going to be dealing with lighting and cameras, and often that works together because if our cameras are functioning at night, whether they be closed circuit television or webcams, we want to make sure we have lighting along with that, the right kind of lighting. We want to make sure we have no dead spots in our cameras and our lighting. Also, we have barricades, we have bollards. The barricades may be out at the perimeter, for example, a gate, a wood gate that comes down, maybe a metal gate, tire shredders, and bollards in front of the entry of our facility. We have different types of fencing, different types of gates and cages. We may have security guards within our facility or maybe at a guard gate at the edge. They may be contractors, they may be employees, they may be armed or unarmed. And along with security guards, we'll have signage. Signs being a key deterrent control. Our most valuable assets, if they fit, will be in safes and secure enclosures, secure closets, for example. We need to protect all of our cable runs, all of our distribution frames throughout our building, our facility. We want to air gap some of our most critical servers, for example. We may have man traps. We'll talk more about that in Course 12. Locking mechanisms and biometrics, tokens, cards, and badges that we use to control physical access. Those same badges can be used to control physical access to different areas or elevators or different buildings or floors. We can also use those same cards or tokens to get access to systems, like our personal computers or our workstations and servers. Various different physical controls will generate different types of alarms. Sensors will send alarms of various types to email, to SMS, to management stations. We may have cable locks, locks on our docking stations for our laptops, and screen filters to block over-the-shoulder reconnaissance. And, of course, fire prevention, detection, and suppression. This is just a quick rundown of techniques and controls that we can use to get physical security. And then, of course, there's logical access. We'll have IPsec and TLS VPN gateways running on routers, firewalls, servers, or specialty appliances. They may also be virtual VPN gateways at a cloud service provider or a SaaS provider. We can use IEEE 802.1x port-based network access control at layer 2. We can have identity and access management, multi-factor authentication, something you know, something you have, and something you are, perhaps a biometric. We can use identity providers, such as Active Directory and Kerberos. In addition, our identity providers may also have federated access to other service providers, for example using SAML 2.0 or OAuth 2.0 and OpenID Connect. And we can control logical access with access keys and secure logical tokens, for example, JSON. In the next lesson, we'll begin our journey through identity and access management. In this lesson, we're going to explore cloud and third-party identity models, and where we're dealing with cloud providers and third parties, more often than not today, we're using hypervisor technology or virtualization. So before we dive into cloud models, let's just quickly define different types of hypervisors. First, we have the Type 1 hypervisors. We also call this native or bare metal. Here, you install the hypervisor software directly onto the hardware. So for example, you would format your solid-state drive and install your open source hypervisor like KVM or Xen, or a proprietary hypervisor. Then, on that hypervisor, you'll install one or more guest operating systems onto the host and possibly applications. Now, the goal of the hypervisor is not just to allow multiple operating systems and applications to run simultaneously, but also to serve as kind of a supervisor, as all the different operating systems and applications share the same finite amount of resources on the underlying hardware, the disk space, the CPU cycles, and the RAM memory, for example. Type 1 hypervisors are the type that are running at your cloud service providers. A Type 2 hypervisor is one you might run on your personal computer. For example, you have the underlying hardware of a workstation or a laptop, and then a host operating system like Linux or Windows. And then you install your hypervisor software, for example, Oracle VirtualBox or VMware Workstation. Notice here our host operating systems running other applications besides the hypervisor, and the hypervisor, of course, can have multiple guest operating systems and multiple applications. You won't get the same kind of performance that you get with Type 1 hypervisors, but they can be very convenient for doing penetration testing, creating sandbox environments, or testing out operating systems and applications before you put them into production. Virtualization has some vulnerabilities. For example, VM sprawl. This is when the number of VMs overtakes the administrator's ability to manage them and the available resources. This can introduce problems like using unlicensed software or downloaded apps. It could be a digital rights management issue or a data leakage issue. It may be against the AUP to even install these Type 2 hypervisors on corporate systems. To avoid VM sprawl, we want to enforce a strict process for deploying VMs, have a library of standard VM images that represent the only authorized images that can be used if we're using hypervisors at all. We want to archive or recycle underutilized VMs and use a virtual machine lifecycle management tool or a cloud service provider managed service. There's also VM escape. This is a huge issue for identity and access management. It's a serious threat where a running process in the guest interacts directly with the host operating system. To protect against VM escape, we want to patch our VMs and VM software on a regular basis. We only want to install what we need on the host and the VMs. Install verified and trusted applications only, for example, only digitally signed applications. And have strong IAM access controls and passwords, preferably multi-factor authentication. In this section of the exam, they also want you to be aware of the different cloud computing service types. This relates directly to identity and access management. According to NIST, IaaS is the capability provided to the consumer to provision processing, storage, networks, and other fundamental computing resources where the consumer is able to deploy and run arbitrary software, which can include operating systems and applications. The consumer with IaaS does not manage or control the underlying cloud infrastructure, but has control over operating systems, storage, deployed applications, and possibly limited control of select networking components, for example, firewalls. When using a cloud provider, you'll be leveraging regions all over the world, and within those regions you have zones or availability zones. Those zones are miles or tens of miles apart, and within those zones you have 2 or more data centers. Cloud providers also have edge locations in metropolitan areas all over the world for content delivery networking. And Amazon Web Services, if you're using infrastructure as a service, they will provide the components at the bottom, the regions, the availability zones, and the edge locations. They'll provide their own identity and access management. They'll provide endpoints to connect to services over their cloud. And of course, their foundation services would be compute, storage, databases, and networking. Everything above that is the responsibility of the customer, including the customer identity access management, either using their IAM components or your own single sign-on solution with your own identity provider. Platform as a service, according to NIST, says the capability provided to the consumer is to deploy onto the cloud infrastructure consumer-created or acquired applications created using programming languages and tools supported by the provider. The consumer does not manage or control the underlying cloud infrastructure, including network, servers, operating systems, or storage, but has control over the deployed applications and possibly application hosting environment configurations. Common platform as a service services would be development and software development kit platforms for Java, PHP, Python, and more. Container services for things like Docker and Kubernetes orchestration. Managed and fully managed relational and document databases. Managed security and threat modeling services. And single sign-on, machine learning, artificial intelligence, Internet of Things, IoT, blockchain, media services, and more. According to NIST, here's SaaS, software as a service. The capability provided to the consumer is to use the provider's applications running on a cloud infrastructure. Think Office 365. The applications are accessible from various client devices through a thin client interface, such as the web browser. The consumer does not manage or control the underlying cloud infrastructure, including network, servers, operating systems, storage, or even individual application capabilities, with the possible exception of limited user-specific application configuration settings. Common SaaS services would be Customer Relationship Management, CRM, human resources and workplace tools, such as a virtual help or service desk, finance, sales, billing, and marketing, email, collaboration, and cloud storage, business intelligence, and security services. We also have cloud provider models. The private model is basically deployed in a sandbox within an organization. A private cloud could be at the provider, or it could be on premises. In the public model, it's deployed by a provider for customer access and consumption. For example, using Amazon Web Services, Google Cloud Platform, or Microsoft Azure. A community cloud is deployed by a consortium in a certain sector, for example, insurance, medical, or government. And then a hybrid cloud is simply a combination of public and or private and or community. In this lesson, we're going to look at fundamental concepts of security models. Security models are used to decide which subjects can access particular objects, the specification of a security policy. Models are typically implemented by enforcing integrity, confidentiality, origin authentication, and non-repudiation controls. The designer will determine how the models will be used and integrated into specific designs, and it may be done by an individual or a committee or a security team. Keep in mind that security is best enforced with a multi-level or hierarchical security system. Let's look at the Bell-LaPadula model. This is the first mathematical model with a multi-level security policy used to define the concept of a secure state machine, models of access, and outlined rules of access. A secure state machine will know every state and all the transactions between those states as related to subjects and objects. The Bell-LaPadula model focuses on ensuring that subjects with different clearances are properly authenticated by having the necessary security clearance, need to know, and formal access approval before accessing an object under different classification levels. All mandatory access control or MAC systems are based on the Bell-LaPadula model because of its multi-level security, and it's been adopted by most government agencies. Bell-LaPadula is a state machine model and is used to control access in complex systems. The state of a machine is collected to verify the security of a system as it defines the behavior of a set number of states, the transitions between those states, and the subsequent actions that can take place. A particular state typically consists of all current permissions and instances of subjects accessing objects. If a subject can access objects only in adherence with the security policy, then the system is considered secure. Here's a simple example of a state machine. State 1 is opened, State 2 is closed. In State 1, our example is to open the door. In State 2, our action is to close the door. And notice the transition conditions are the transitions between the opened and closed state. The same thing applies to subjects and objects and the transitions between those states in a MAC model. Bell-LaPadula has a rule set. First is the simple security rule. A subject at a given security level, for example, an agent at a government agency, cannot read data that resides at a higher security level. That's the no read up rule. The star property or asterisk rule states that a subject at a given security level cannot write information to a lower security level. That's the no write down rule. The strong star property rule states that a subject who has read and write capabilities can only perform those functions at the same security level, nothing higher and nothing lower. And then there's the tranquility principle. Subjects and objects cannot change their security levels once they've been instantiated. Keep in mind that Bell-LaPadula is a confidentiality model, and there can be exceptions to these rules as long as it's decided upon by the security team or the committee before the model is implemented. The BIBA model is an integrity model. It was developed after Bell LaPadula, and it uses a lattice of integrity levels, unlike Bell LaPadula. It has the simple integrity rule, or no read down. This rule states that a subject cannot read data from a lower integrity level. The star integrity rule, no write up, maintains integrity by stating that a subject cannot write data to an object at a higher integrity level. The invocation property states that a subject cannot invoke or call upon a subject at a higher integrity level. BIBA, or BIBA, is also an information flow model, like Bell LaPadula, because they're most concerned about data flowing from one level or one sensitivity level to another. For example, secret to the level top secret above it, or secret to the level SBU, sensitive but unclassified, below it. An information flow model observes information flows in a state machine. Data is considered in individual discrete compartments based on classification and need-to-know principles. Subject clearance overrules the object classification, and the subject security profile must contain one of the categories listed in the object label that enforces need to know. For example, Bell LaPadula model prevents information flowing from higher source levels to lower source levels. The BIBA model prevents information flowing from lower integrity level to higher integrity levels. Often, an information flow model and other models will be expressed in lattices or in matrices. For example, here we can see that there's a bidirectional information flow between A and C, but only a unidirectional flow from B to C and C to D and A to D. There is no flow whatsoever between A and B. Any information flow outside of this model is referred to as a covert channel. There's also the Clark-Wilson integrity model. This was developed after BIBA and deals with information integrity. Objects can be modified by subjects using read-write operations. Integrity verification procedures, IVPs, are programs that run periodically to check the consistency of the integrity rules, the CDIs, that are usually defined by vendors. The integrity goals of Clark-Wilson model are to prevent unauthorized users from making modifications, and further, to ensure separation of duties prevents authorized users from making improper modifications, and ensure well-formed transactions, maintaining internal and external consistency. Let's look at access control methodologies now, starting with a very popular role-based access control, otherwise known as RBAC. With RBAC, access decisions rely typically on organizational chart, or the established roles and responsibilities of individuals in your organization, or perhaps a location in a user base, in a directory, for example, like Active Directory. The role is typically set based on evaluating the essential objectives and architecture of the enterprise. An RBAC framework is determined by security administrators and officers, or possibly server admins, but it's not at the discretion of the user. It's often built into the framework or the platform. For example, in a relational database management system, you may have pre-established roles. Another example is in a medical center, where your different roles may be doctor, RN, PA or physician's assistant, specialist, technician, attendant, receptionist, and others. Each one of these roles can have rights and permissions assigned to it. Then, when a new specialist is hired at the medical center, they immediately are placed into that group or that container, and they inherit those rights and permissions. We're seeing companies with a lot of turnover, or lots of transient, temporary, and contractor users move from a discretionary access control model that we'll see here in a moment to a role-based, due to the flexibility and easier management. The advantages of role-based access control is that it's easy to implement and control. Often the roles can be assigned using written security policy. Also, RBAC is built into many security frameworks, such as database management systems, or IAM, Identity and Access Management, at cloud providers like AWS and Google Cloud Platform. It often easily aligns with accepted security principles. Some disadvantages, however, are the fact that scope creep or privilege creep can take place over time. Therefore, the roles and access must be rigorously audited. Also, if there's multi-tenancy capabilities, we need things like Active Directory organizational units or cloud provider organizational units to group up multiple accounts. Our next access control methodology is rule-based access control. Rule-based access control uses acronyms like RBAC or RB-RBAC. Rule-based often dynamically assigns roles to users based on criteria defined by the custodian or the system administrator. A rule could also be a time-based access control list. For example, if network time protocol is being used, so you can control access to a particular drive object during only business hours. For example, 6 a.m. to 6 p.m., Monday through Friday. Rule-based access controls are common for infrastructure devices like routers, switches, firewalls, and appliances to use rule-based access controls. So, for example, you could have a list of numbered entries where you're going to permit TCP-based HTTP, HTTPS, and FTP control and data from any network to servers 10.10, 10.11, and 10.12. As the packet comes inbound to the router, it examines the metadata or the header information of IP and TCP and compares that information to this numbered list. Once there's a match, it will take the action, for example, permit, and then move on to the next datagram or packet. If none of the rules match, at the end of the list, there is an explicit deny any with a log entry so that deny will be sent to a syslog server. You can also use rule-based access controls at cloud providers. Here's an example of a network ACL, or Network Access Control List, at Amazon Web Services. You can see the type of protocols and services that you can match on. Some of these are standard ports like POP3 110, IMAP 143, LDAP 389. Some of these, however, are going to be specific to the cloud provider. For example, Redshift using port 5439 for data warehousing. You also determine port ranges, the source IP address prefix in a CIDR format, and your allow or deny action. Again, rule-based access controls are a static or a stateless access control mechanism. Next, we have mandatory access control, or MAC. Now, we actually covered these earlier in the course when we talked about Bell LaPadula and Biba and Clark-Wilson. Those are all MAC models. However, MAC is a strictly non-discretionary methodology, and it secures data by assigning sensitivity labels and then compares those labels to the level of user sensitivity. It is appropriate for extremely secure systems, such as multi-level secure military applications or government agencies. These organizations use classification levels like top secret and secret and confidential. Its main advantage is that the MAC model is based on a need to know, and it's strictly adhered to. Therefore, scope creep or privilege creep is minimized. All MAC systems are based on the Bell LaPadula model for confidentiality. This was the first mathematical model with a multi-level security policy used to define the concept of a secure state machine and models of outlined rules of access. A MAC model is non-discretionary. There is no owner of an object who can determine other permissions or file sharing on that object. The state machine is determined by committee or by a security team before any subjects begin to access any objects. One of the most common models used, especially in commercial environments, is the discretionary access control, or DAC. In this model, DAC restrict access to data in systems based on the identity of users and/or their group membership, often in some type of directory service, for example, Active Directory. Access results are usually based on authorization granted to a user based on the various forms of credentials presented at the time of authentication. For example, an Active Directory would often be a Kerberos ticket. In most DAC implementations, the owner of the resource can actually change its permissions at their discretion, or grant access to that object or shares to that object, in addition, share permissions. A DAC framework can deliver the capability for granular access control. Advantages to DAC is that it's easy to implement and operate, often very intuitive. It aligns with the least privilege security principle when properly implemented, and the object owner can have a lot of control over granting access. This can encourage interoperability and productivity, especially in a flatter organization or a projectized organization. Some disadvantages, however: documentation of the access must be strictly maintained. In other words, an active change and configuration management database. And the discretionary access model has the highest propensity for privilege or scope creep compared to all of the other models. In this short lesson, we'll talk about a very important and popular form of access control known as ABAC, attribute-based access control. ABAC goes further by controlling access to entities by weighing rules against the attributes or characteristics of the subject's actions and the actual request environment. For example, is it in a VPN or is it not? Is it local access? Is it remote access? ABAC relies upon the evaluation of people's characteristics, attributes of IT components. For example, what are you accessing and when? It could use heuristic engines. It can take in environmental factors and other situational variables. Often, we used advanced IAM systems, such as Cisco's Identity Services Engine and other tools, to create authorization profiles based on a wide variety of different variables. And the beauty of ABAC systems is they can enforce both discretionary access control, DAC, as well as strict mandatory access control models. In fact, we're starting to see more ABAC being used in government and military MAC implementations. Next, let's talk about another emerging modern method for access control known as risk-based access control. This is also referred to as risk-adaptable access control, or RADAC. Risk-based considers the obstacles of traditional access control approaches to sharing of information. It's a model that seeks to imitate real-world decision-making while considering operational needs and security risks together with every access control decision. RADAC realizes that situational conditions will drive the relative weight of these two factors when authorizing access. RADAC can support extremely restrictive policies, as well as those that offer the broadest sharing, with added risk, under specific conditions. Here we see a possible flow chart. Let's assume there's an access request. First, we'll determine the security risk, typically using some type of quantitative mechanism, like open fair, factor analysis of information risk, perhaps using PERT and Monte Carlo simulations. Then in step 2, we'll determine if the security risk is acceptable based on our policy. If it is acceptable, we'll go to step 3, where the policy requires verification of operational need. Then, in step 5, we'll assess the operational need. If the security risk in step 2 is not considered acceptable, then we'll go to step 4, where the policy allows for operational need to possibly override the security risk. If you can, then we go to step 5. Let's assume in step 4 that the policy doesn't allow us to override the security risk, or it's false. Then we will deny access and go to post-decision processing. Going back to step 3, if the policy requires verification of an operational need, we then go to step 5 and assess the operational need, and then in step 6, we determine if the operational need is sufficient per policy. If it's not, we deny access. If it's true, then we grant access. Notice, regardless of whether we grant access or deny access, there is post-decision processing, which leads to continual improvement, or lessons learned. In this course, Identity and Access Management Principles, you learned about controlling physical and logical access, virtualization and cloud service types and deployments, security models, and access control models. In the next course, we'll explore authentication and authorization protocols, provisioning and deprovisioning entities, and implementing identity management (IDM) and multi-factor authentication.